At 6 o'clock a.m. Pacific Daylight Time today, Voyager is 576,000 kilometers above the swirling cloud tops of Neptune and traveling away from that distant planet now.
Yes, we were actually quite surprised at how intense the signature was, and it was distributed much further from where we thought the ring plane would be than we expected.
This is Neptune, the last great planet before our familiar map dissolves into darkness and drifting ice. When Voyager 2 swept past in 1989, it gave us our only close look, one brief encounter with a world that does not grant second chances. The images were beautiful and the data were unsettling, because the calm face hid a system in motion. Measured in infrared, the planet radiates more energy than it receives, as if a furnace still burns beneath the cloud deck. The deeper we descend, the less Neptune resembles a distant sibling of Earth, and the more it becomes a laboratory for alien physics. In that pressure-crushed mantle, ice can behave like fire, molecules break, ions roam, and oceans may conduct electricity like metal. Somewhere in that darkness, carbon may be forced into new forms, sinking through a convecting world as gravity sorts matter into order. So we begin at the blue horizon, where the planet looks quiet, and we listen for what the silence hides. We will trace the light that reaches Neptune, the heat that escapes it, and the forces that turn cold air into supersonic motion. And as the visuals carry us from luminous cloud tops into a black interior, one possibility will steadily emerge. The edge of the solar system is not an ending, but a machine. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We will move from Neptune's deceptive colour into its supersonic winds, vanishing storms and hidden heat, then descend toward a crooked magnet and stranger chemistry. Finally, we will pull back to Triton and the rings, where Neptune's history leaves evidence written in orbit. Neptune hangs at the edge of our familiar map, a blue point suspended in long dusk. It orbits about 30 astronomical units from the Sun, nearly 3 billion miles out, where the solar system thins into darkness. Sunlight there is thin and weak, roughly 1/900th of what Earth receives, so even noon feels like a perpetual late evening. The Sun is no longer a warm disk in the sky, but a brilliant star that offers light without comfort. Near the cloud tops, the average temperature sits near 70 Kelvin, about -200 Celsius, cold enough to make ordinary gases behave strangely. Methane can condense into icy crystals, and hazes can form from photochemical reactions that barely proceed in the weak light. By every simple expectation, a world that cold and dim should be quiet, slow, and nearly inert. Yet Neptune refuses to behave like a frozen relic, and that refusal is visible in motion. The planet looks serene from afar, a peaceful blue jewel in the black with a colour that seems almost painted. That calm is an illusion that collapses the moment we measure motion and pressure, because the atmosphere is not resting. Neptune drives winds that can exceed the speed of sound, racing around the globe in broad, curving bands. In places, those winds reach well over 1,000 miles per hour, fast enough to outrun hurricanes by an order of magnitude. It builds massive storms that rise and fade like bruises in the atmosphere, dark ovals edged by bright high clouds. It sustains violent weather systems in a place where sunlight should barely matter, and it does so year after year. This contradiction is the first terror of Neptune, because it breaks our intuitive accounting of energy. The farther we go from the Sun, the less energy is available to stir an atmosphere, and the less chemistry is driven by light. Jupiter and Saturn have internal heat, but Neptune pushes the paradox into sharper relief because it is smaller and farther away. Neptune radiates much more energy than it receives from the Sun, meaning it shines in infrared like a body with its own furnace. Measurements suggest it emits roughly 2 to 3 times the energy it absorbs, a surplus that must come from within. Something inside is generating heat, then feeding it upward into weather that should not exist. The mystery is not only meteorology, because winds are just the surface expression of deeper physics. It is a question about how planets work when the usual rules are starved of fuel, and when distance turns the Sun into a weak lamp. If Neptune is cold at the top, what is happening below, where pressure rises and materials change their nature? What engine turns faint sunlight into the fastest winds in the solar system, And why does that engine not stall? What hidden structure can store heat for billions of years, then release it through storms that blossom and vanish? And what does that interior do to matter, when pressure and chemistry rewrite the familiar states of ice and rock? Even the word ice misleads us here, because in planetary science it means something broader than frozen water. In Neptune's depths, ices include water, ammonia, and methane compounds, mixed and compressed until they become dense fluids. Under immense pressure, water can enter exotic phases, including forms that conduct electricity, which matters for magnetic fields. Carbon-bearing molecules may break apart, and carbon could crystallize, possibly forming diamond-like structures that sink through heavier layers. These are not poetic ideas, but consequences of phase diagrams, where temperature and pressure decide what matter can be. Neptune is a laboratory, where those diagrams are tested at scales no Earth experiment can fully reproduce. Neptune also carries a human story that begins with a different kind of storm, one made of numbers and frustration. In the early 19th century, astronomers tracked Uranus and found its orbit misbehaving, drifting from the path predicted by Newton's laws. The deviations were small but persistent, and they resisted easy explanation even after careful revisions of tables. Some suspected errors in observation because telescopes and timing were still imperfect, and old data could be inconsistent. Others wondered if Newton's law might fail at great distance, a radical thought in an era that trusted mechanics. But a few took the riskier path and proposed an unseen planet tugging from beyond, a hidden mass shaping Uranus by gravity alone. Two mathematicians, working separately, turned those irregularities into a prediction, and they did it with astonishing discipline. Urbain Le Verrier in France and John Couch Adams in England calculated where a new world should be, using perturbation theory to infer an unknown body. They treated Uranus as a test particle being pulled off course, then worked backward to estimate the disturber's orbit and mass. Their methods differed, their timelines collided, and their credit would be debated for generations, coloured by national pride and institutional politics. But the core idea held, and it was audacious in its simplicity. Gravity could reveal a planet before any telescope saw it. In 1846, the prediction met observation, and the moment felt almost like a conjuring. Johann Galle in Berlin received Le Verrier's letter and pointed a telescope near the calculated position on the ecliptic. He and Heinrich de Rest compared the sky to star charts, using careful positional astronomy rather than lucky scanning. They found a point that did not belong, a star that was absent from the map and too steady to be a comet. Night to night it moved against the background stars, slow but undeniable, and the new planet stepped out of mathematics into sight. Neptune was discovered not by chance, but by mathematics made visible, an idea that still defines modern astronomy. That origin story matters because it frames Neptune as a triumph of physics, a victory for prediction over darkness. The same laws that guide falling apples and orbiting moons reached into the outer solar system and found a planet, as if the equations themselves had eyes. But Neptune also became a challenge to those laws in practice, because prediction is easier than explanation. Once found, it did not simply complete the solar system's inventory, adding another dot to a chart. It opened a new category of worlds and a new set of unanswered questions about composition, climate, and interior energy. It also hinted that our solar system's architecture was not finished being understood, even after the map looked complete. From Earth, Neptune remains distant and stubbornly small, a target that resists intimacy. Even large telescopes reduce it to a disk with subtle bands and occasional dark features, softened by our own atmosphere's blur. We can measure its colour, its seasons, and the broad chemistry of its upper atmosphere through spectroscopy. We detect methane, which absorbs red light and leaves the reflected sunlight enriched in blue, creating Neptune's deep oceanic hue. We can estimate its mass and density from its gravitational pull on moons and from its effect on spacecraft trajectories. Those numbers tell us it is not a gas giant like Jupiter, dominated by hydrogen and helium all the way down. It is an ice giant, built from water, ammonia, and methane compounds mixed with rock and hydrogen, layered in ways that are still debated. But inference is not intimacy, and Neptune has offered us very little direct evidence. Almost everything we claim to know in detail comes from a single encounter. In 1989, Voyager 2 swept past Neptune on a one-time flyby, the last planetary visit of its grand tour. It did not enter orbit, and it did not return because its speed and power budget made lingering impossible. It arrived, observed, and left, carrying a brief harvest of images and measurements stored on tape and sent home across billions of miles. At Neptune's distance, radio signals take hours to reach Earth, and the data rate is painfully small by modern standards. For Neptune science, that short window is still the closest look humanity has ever taken. Voyager 2 showed a planet that looked alive, not merely rotating but actively reshaping itself. It revealed a deep blue atmosphere shaped by methane absorbing red light, with bright clouds that stand out like chalk on cobalt. It found powerful winds and rapidly changing cloud features, including thin streaks that suggest strong vertical shear. Some clouds appear to be methane ice lofted high above darker layers, where sunlight is even weaker and temperatures are lower. It saw a large dark storm system, later called the Great Dark Spot, a vast anticyclone with a rotating structure like a planetary scale wound. Bright companion clouds formed near it, likely where air was forced upward and cooled, then condensed into reflective crystals. Voyager watched those features shift and stretch over hours, a reminder that Neptune's atmosphere is not static even on human timescales. The spacecraft measured temperatures and pressures in the upper layers, building vertical profiles that hinted at complex circulation. It found that Neptune's stratosphere is warmer than simple sunlight heating would suggest, implying energy transport from below or absorption by hazes. It mapped a magnetic field that was strangely tilted and offset. Unlike the relatively centered dipoles of Earth and Jupiter, Neptune's magnetic axis is inclined by dozens of degrees from its rotation axis, and the field appears displaced from the planet's center. That geometry suggests the Dynamo does not operate deep in metallic hydrogen, as it does in Jupiter, but in a shallower shell of electrically conducting fluid. In other words, Neptune's magnetism points to an interior that is layered in unexpected ways. Voyager 2 confirmed rings that are thin, dark and clumpy, with a texture that feels unfinished. The rings are not bright like Saturn's, but dusty and low in reflectivity, making them difficult to see except at the right angles. Most striking were arcs, localized concentrations of ring material that should disperse over time as particles spread along their orbit. Their persistence implies gravitational shepherding, likely by nearby moons, locking particles into resonant patterns. Even here, Neptune is not passive, because its gravity and satellites sculpt structures that should otherwise smear into uniformity. The rings become another clue that the system is dynamic, maintained by delicate balances rather than permanence. Voyager 2 also expanded Neptune's family, and in doing so it broadened the meaning of activity so far from the Sun. It flew past Triton, a large moon with a retrograde orbit, moving opposite Neptune's rotation like a captured intruder. That backward path strongly hints at capture from the Kuiper Belt, a region of icy bodies beyond Neptune that preserves early solar system material. Capture is not gentle, and it likely involved energy lost through interactions, possibly with other moons that were ejected or destroyed. Triton's surface is coated with nitrogen ice, with plains and ridges that suggest resurfacing rather than ancient stagnation. Voyager saw plumes rising from Triton's south, like geysers driven by weak sunlight and internal processes, casting dark streaks across the ice. In Neptune's realm, even moons can be unexpectedly dynamic, as if the cold itself hides motion. But Voyager's gifts came with sharp limits, because a flyby gives a snapshot, not a full story. It sampled one season, one hemisphere in detail, and one moment in a planet's long climate cycle, which unfolds over decades. Neptune's year lasts about 165 Earth years, so a single visit catches only a thin slice of seasonal change. Voyager watched storms for days, not years, and could not track how they are born or why they die. It could not measure deep winds because cloud tracking reveals only the motion of the visible layers. It could not map the interior structure directly because gravity and magnetic measurements were brief and limited by trajectory. It could not resolve the layers where heat is generated, stored and transported, which is where the real engine must live. That scarcity of data is part of Neptune's power over our imagination, because the unknown is not empty. We have a planet that behaves like a raging engine, yet we have only a brief close-up record, like a single photograph of a storm at sea. We can model, extrapolate and argue, building simulations that reproduce some features while failing at others. We can compare Neptune to Uranus, which is similar in size yet radiates far less internal heat, sharpening the mystery by contrast. Why should two ice giants, born in the same outer region, diverge so dramatically in energy output and weather? Neptune is both well-known and barely known, a paradox in our knowledge as well as in its physics. The central question of this documentary begins here, in that gap between appearance and reality. How can a world so distant and dim generate winds that outrun sound and keep them organised into global patterns? How can it sustain colossal storms when sunlight is almost irrelevant and when the upper atmosphere is colder than dry ice? What internal heat source drives the excess energy Neptune radiates into space, and how efficiently is that heat transported upward? And what does that energy do to the materials inside, where pressure may force carbon into diamonds and water into exotic conductive forms? If we could descend, what would ocean even mean in a place where water is not liquid in the familiar sense? Neptune's remoteness is not just a fact of distance, because it is a barrier that shapes every conclusion we draw. At 30 astronomical units, communication is slow, missions are rare, and sunlight is too weak for easy power, pushing spacecraft toward radioisotope systems. The cold that defines the cloud tops also challenges instruments and assumptions because lubricants, electronics, and detectors must survive deep freeze. Even the planet's day and tilt complicate long-term monitoring from Earth, because changing geometry hides and reveals features. Neptune rotates in about 16 hours, so storms evolve under rapid spin, and that rotation helps organise winds through the Coriolis effect. The planet's axial tilt gives it seasons, but those seasons are slow, and patience becomes part of the science. Still, the evidence we do have is enough to demand an explanation, because the signals are too strong to ignore. Neptune's winds are not a minor anomaly, but a signature of deep energy flow, implying that momentum is being supplied and maintained. The storms are not decorative, but structural, tied to heat transport and atmospheric chemistry, and perhaps to the condensation of methane and other volatiles. The magnetic field is not a simple dipole, but a clue that the dynamo operates in an unusual layer, where conductivity and convection overlap. Each observation points downward, toward an interior we cannot see, and toward processes that are hidden by thousands of miles of opaque fluid. So Chapter 1 sets the stakes, and it does so with a planet that refuses to sit quietly at the end of the map. Neptune is not a quiet endpoint of the solar system, a final ornament beyond Saturn's grandeur. It is a laboratory of extremes, running on an unknown engine in perpetual twilight, where the sun is present but not dominant. Its beauty is real, but it is deceptive, because the calm colour hides violence and speed, and the stillness is only apparent. Its discovery was a victory for prediction, but its behaviour now tests what prediction can do when data are scarce. Neptune asks whether we truly understand how planets store heat, move energy, and build weather in the cold. From here, we move from the surface impression to the mechanisms underneath. We follow the chain from faint sunlight to furious winds, from blue haze to dark storms, from a tilted magnetic field to a hidden ocean of exotic fluids. We begin at the cloud tops, where methane and hydrogen swirl in thin sunlight, and where winds carve patterns across the globe. Then we descend, layer by layer, into the blue abyss that Voyager only skimmed, toward the pressures where matter becomes unfamiliar and the planet's secret heat is born. Descending through the cloud tops, the distinction between gas and liquid becomes meaningless. There is no solid surface to stand on, no sudden splashdown into an ocean. Instead, the pressure climbs relentlessly until the hydrogen and helium atmosphere compresses into a supercritical fluid, a state of matter where distinct phases dissolve. Deep within this crushing darkness, thousands of miles down, lies the Mantle, a vast region that challenges our understanding of physics. Here, the mixture of water, methane, and ammonia is subjected to pressures millions of times greater than atmospheric pressure on Earth, forcing matter into exotic configurations that exist nowhere else in nature. The most bizarre of these states is superionic water. In the deep mantle, extreme pressure breaks the molecular bonds of water. The oxygen atoms are forced into a rigid crystal lattice structure usually associated with solids, while the hydrogen nuclei flow freely through this lattice like a liquid. This creates a substance that is simultaneously solid and liquid, black in colour and extremely hot. This superionic ice is electrically conductive, behaving more like a metal than water, and its churning motion is likely responsible for generating distinct aspects of the planet's electromagnetic environment. Further complicating this internal soup is the potential for diamond precipitation. As the pressure bears down on the methane molecules deep within the mantle, the carbon atoms are stripped away and crushed together. Theories suggest that these carbon atoms crystallize into diamonds, which then rain down through the fluid layers like hailstones. As these diamonds fall toward the core, they generate friction and heat, converting gravitational potential energy into thermal energy. This mechanism offers a compelling explanation for the planet's excessive internal heat radiation, essentially describing a world that is kept warm by a perpetual storm of falling diamonds. The chaotic motion of these conductive fluids generates a magnetic field that is profoundly broken. Unlike Earth's magnetic field, which aligns roughly with the rotation axis and originates from the core, Neptune's field is tilted at a staggering 47 degrees and is offset from the planet's physical centre by nearly half a radius. This suggests that the dynamo generating the field is not deep within the core, but is instead produced in a thin, unstable shell of conducting fluids closer to the surface. It portrays a planet that is lopsided and turbulent on the inside, a dynamo that is constantly twisting and turning upon itself. Orbiting this chaotic engine is a system that speaks to a violent history. The ring system is clumpy and uneven, dominated by distinct arcs rather than uniform bands, held in place by the gravitational shepherding of small moons. But the true anomaly is Triton, Neptune's largest moon. Triton orbits in retrograde, moving opposite to the planet's rotation, a clear indication that it did not form with Neptune but was captured from the Kuiper Belt billions of years ago. This capture event would have been cataclysmic, likely shattering Neptune's original moon system and scattering the debris that now forms the tenuous rings. Triton remains a prisoner of gravity, slowly spiralling inward, destined to one day be torn apart by the very planet it orbits, adding a final, violent chapter to the history of the hidden machine. Neptune's first trick is simple, and it works because our eyes love shortcuts. It convinces us that colour is knowledge, and that seeing blue means seeing a world. From Earth, and even from Voyager, we meet a disk and a hue, an icon more than a place. We call it an ocean planet, then we forget it is mostly gas, and that the surface is only a moving boundary. Neptune's atmosphere is dominated by hydrogen and helium, the two lightest elements in the universe. Those gases form the bulk of the visible envelope and the pressure-bearing air, and they behave like a vast cold laboratory for fluid physics. Mixed into that hydrogen and helium is methane, present in small fractions that still matter enormously. Methane matters because it reshapes the sunlight that returns to us, and because it advertises chemistry we cannot otherwise see. Sunlight arrives already weak, then Neptune filters it again through layers of gas and haze. Methane absorbs red wavelengths more efficiently than blue, so the reflected light skews toward blue and leaves our cameras with an exaggerated impression. That is the core of Neptune's visual identity, and it is a physical process rather than a pigment. The planet is not painted blue. It is selectively subtracting colours from a dim lamp, like a stained glass window that removes warm tones. If you could hover above the clouds, the light would feel thin and distant, as if the sun were a bright star rather than a day. At Neptune's orbit, the solar energy is only a tiny fraction of what Earth receives, so every photon that returns has been carefully sifted. Uranus also contains methane, yet it often looks paler and greener in many images. The difference is not a single ingredient, but a different atmospheric recipe and structure that changes how light is scattered before it escapes. Neptune's deeper blue likely reflects less high-altitude haze that would otherwise brighten and wash out the disk. It also reflects more contrast from deeper, darker layers beneath the cloud tops, so the planet reads as richer and more saturated. Haze is not just smog, and it is not merely cosmetic. Tiny aerosol particles scatter sunlight in ways that depend on size, shape, and wavelength. Small grains tend to scatter blue light efficiently, which can either brighten a planet or mute its contrasts. Temperature and circulation also change the balance, and they do it subtly. If methane is mixed differently with height, the absorption path length changes and the colour deepens, because photons travel through more methane before returning to space. Even the viewing geometry matters, and Neptune reminds us of that with every telescope image. At different phase angles, light skims through different thicknesses of atmosphere, and the same planet can appear slightly different simply because the photons took a longer route. So the blue is real. But it is not a surface, and it is not a single layer. It is an optical outcome of chemistry, altitude, particle scattering, and the angle of sunlight. An emergent colour built from invisible decisions. The second trick is texture, and it is just as persuasive as the colour. Neptune shows bands, bright clouds, and occasional dark ovals, and we assume we are watching the atmosphere as a whole. In reality, we see only the uppermost layers that can scatter light back to space. A thin slice of a much deeper system. Everything below becomes hidden as pressure rises and opacity thickens, and the visible world becomes a lid over a deeper engine. Neptune's cloud architecture begins with hazes at high altitude, where the air is extremely tenuous and cold. These are thin layers of complex hydrocarbons produced by sunlight-driven chemistry in the upper atmosphere, and they can spread like a faint veil across the globe. Even faint sunlight can break methane apart over long timescales, because ultraviolet photons carry enough energy to snap molecular bonds. The fragments recombine into heavier molecules that form aerosols, creating a veil above the main clouds and softening the planet's sharpest contrasts. In a close-up, that haze would look like a delicate mist lit from above, bluish, translucent and uneven. It is the kind of layer that makes edges look gentler, and it can hide the true depth of whatever churns beneath. Below the hazes, methane can condense into ice clouds, but ice here means crystals suspended in a hydrogen-rich sky. Where air rises and cools, methane reaches saturation and forms reflective grains that catch the weak sunlight like snow in a twilight. Those methane clouds are often what we track in visible images, because they are bright and relatively high. They sit where sunlight still reaches and scattering is efficient, so they become natural tracers for winds that we cannot otherwise touch. When those clouds race across the disk, their motion is not just weather in the everyday sense. It is the visible signature of momentum and heat, moving through a rotating fluid, shaped by Neptune's rapid spin and the Coriolis forces that organize flow into bands. Deeper down, other cloud decks are expected, layered by chemistry and pressure, like chapters we cannot open. Hydrogen sulfide and ammonia compounds may condense at different pressures, depending on the temperature profile, and each deck changes how radiation moves upward. At still greater depths, water becomes relevant, but not as familiar droplets falling through air. Under those pressures, water behaves as a dense fluid and can form exotic phases, and the line between ocean and mantle becomes a matter of thermodynamics. The key is the temperature profile with height, which acts like a map of where condensation is allowed. As pressure increases downward, temperature generally rises, and each condensable species has a level where it can form clouds, provided the air can cool enough. Clouds are therefore not decorations, and they are not merely scenic highlights for a camera. They are thermodynamic markers, and each bright patch hints at a boundary where chemistry and temperature intersect in a narrow zone. Neptune's visible features also depend on vertical motion, which is harder to see than horizontal winds. Upwelling cools air and makes clouds, while downwelling warms air and clears them, and the planet's face changes as those motions migrate. That's why dark regions can appear, and why they feel like openings into something deeper. They may be windows into lower layers, or regions where aerosols and clouds are suppressed by sinking air that dries and warms the column. The great dark spot seen by Voyager was not a hole to the interior, even if it looked like one. It was a storm system that changed the cloud field above and around it, a vortex whose influence reached beyond its visible boundary. Historically, that Voyager moment mattered because it broke expectations built from distance. Before 1989, Neptune was a remote blue dot, and then a spacecraft revealed a world with active weather, high-contrast storms and clouds that shifted in mere days. Bright companion clouds near dark storms are a clue to uplift, and they behave like banners in a fast wind. Air forced upward cools rapidly, methane condenses, and the resulting clouds trace the storm's circulation, bright arcs that appear, stretch, and dissolve. Even this explanation hides a limitation, and the limitation is fundamental to astronomy. We infer vertical structure from brightness and spectra, but we cannot directly sound most depths, so we translate light into physics and accept the uncertainty. Remote sensing is our main tool, and it has rules that can be stated plainly without reducing the wonder. We learn from light that is reflected and from light that is emitted, and each kind of light carries a different story. In visible wavelengths, Neptune mostly reflects sunlight, and the signal is shaped by the topmost layers. The patterns we see are shaped by cloud reflectivity, haze scattering, and methane absorption, which together decide which photons return and which are swallowed. In infrared, Neptune can glow with its own heat, and that glow is a different kind of evidence. Thermal emission carries information about temperature and about gases that absorb and emit at specific wavelengths, so the planet becomes a map of energy rather than colour. Different wavelengths probe different altitudes, and that is one of the quiet miracles of spectroscopy. Some bands escape from higher, colder layers, while others emerge from deeper, warmer regions, because gases and aerosols block some colours more than others. Spectroscopy turns colour into composition, and it does so with mathematical precision. Each molecule leaves a pattern of absorption lines that acts like a fingerprint, even when the planet is a tiny disk and the light has crossed billions of kilometres. Methane's fingerprint is especially important in the near-infrared, where its absorption is strong and structured. It blocks light so efficiently that bright clouds in those bands must be high, above much of the methane, or else they would vanish into darkness. That is how we estimate cloud heights without touching them, and the logic is surprisingly direct. A cloud that stays bright where methane should absorb must be sitting at low pressure, because there is less methane above it to erase the signal. Thermal infrared adds another dimension, because brightness becomes a proxy for temperature at a given level. If a region is warmer at a given pressure level, it emits more, and we can map temperature contrasts across the disk and watch them evolve. Temperature maps reveal circulation indirectly, which is both powerful and incomplete. Warmth can indicate sinking air and compression, while cool regions can indicate rising air and expansion, so the thermal picture becomes a shadow play of vertical motion. But remote sensing also forces humility, and it forces it every time we turn spectra into profiles. Every measurement is filtered by radiative transfer, and radiative transfer depends on assumptions about aerosols, cloud particle sizes, and how gases are mixed. We build models of how photons move through gas and haze, and we test them against the data. Then we adjust those models until the observed spectrum matches, and we call the result a profile, an inference that is rigorous yet never fully unique. This is powerful, but it is not the same as a probe descending through the layers and tasting the air. It is a reconstruction, and multiple interiors can sometimes produce similar spectra, so certainty has to be earned rather than assumed. Neptune's distance makes the problem harder, and it punishes sloppy thinking with noise. The sunlight is about 1/900th of Earth's, so the reflected signal is faint and the noise matters, especially when we chase subtle contrasts. Weak sunlight also changes the planet itself, not just our measurements of it. If solar energy were the main driver, Neptune's weather should be sluggish, with small temperature contrasts and gentle winds that fade into a cold equilibrium. Instead, Neptune shows extreme winds and rapid cloud evolution, even at latitudes where sunlight is scarce. The visible atmosphere behaves like it is being powered from below, not merely stirred from above, and that reversal is the chapter's hidden hinge. The winds we infer from cloud tracking can reach extraordinary speeds, and that fact carries an implication. Fast winds require sustained energy and a way to move momentum through the atmosphere, so the planet must have a mechanism that keeps the system from settling. The energy budget makes that tension explicit, and it does so in a single comparison. Neptune emits more energy than it absorbs, so it must be releasing internal heat into space, and that surplus heat is a measurable, persistent glow. That internal heat leaks upward through convection and waves, and it does not rise smoothly. It can warm the deep atmosphere, steepen temperature gradients, and feed storms that sunlight cannot sustain. An engine that runs in the dark. This is where Neptune's blue mirage becomes dangerous to our intuition. The calm colour is a thin skin over an engine, and the engine is mostly invisible, so the planet's serenity becomes a kind of misdirection. When we look at Neptune in visible light, we mostly see cloud tops near a fraction of a bar, comparable to the pressures where aircraft fly on Earth. That is a boundary layer, not the planet's body, and it is only a small fraction of the total mass above the interior. Below those clouds, pressure rises quickly, and the scale of change is unforgiving. In tens of kilometers, conditions shift enough to change chemistry, opacity, and the way heat moves, so the atmosphere becomes less like air and more like a compressed fluid. Below that, the atmosphere transitions into a deep fluid envelope, and the word sky starts to fail. Hydrogen and helium remain present, but heavier molecules become more important with depth, and the mixture grows denser, hotter, and more conductive. At some point, the word atmosphere becomes misleading because the familiar categories dissolve. The gas becomes a dense, hot mixture where distinctions between gas and liquid blur and where weather is inseparable from the planet's interior physics. We cannot see that region directly, yet it controls what we do see, and it does so continuously. It sets the stability of layers, the supply of condensables, and the pathways for heat. So the visible clouds are like foam on a deep-moving sea. Neptune's storms therefore become surface symptoms, and that framing changes how we read the images. A bright cloud is a sign of uplift, but the uplift may be driven by heat far below the visible deck, rising until it finally condenses into something we can see. Even the planet's colour can be influenced by deep processes, which is part of the trick. Vertical mixing can change methane's distribution, and haze production can change how much blue escapes, so the look of Neptune is tied to dynamics as well as chemistry. Comparisons with Uranus sharpen the mystery because the two planets are siblings in mass and size. Uranus is similar in composition, yet it radiates far less internal heat and often looks more muted, as if something is damping its interior-to-sky connection. That suggests different interior histories or different barriers to heat flow, and the difference may be structural. A stable layer can trap heat like insulation, while a more convective interior can leak it upward, and the atmosphere above will respond in visible ways. Neptune appears to be the leaky one, and that leak is a clue rather than a defect. Its excess heat is not just a number, it is evidence that the interior is still active, still cooling, and still capable of driving motion in the visible sky. So what do we really see when we look at Neptune, and what do we only think we see? We see sunlight reflected by a few cloud layers and filtered by methane and hazes, and we translate that filtered light into a story about structure. We see patterns shaped by condensation physics and by winds that we track at the top, where traces are available. We do not see the deep circulation that may carry most of the energy, and we do not see the layers where composition may change dramatically. We see a planet that is optically thin only in a narrow range of heights, a thin corridor of visibility. Beneath that range, photons are trapped and information becomes indirect, so the planet becomes less an image and more a set of constraints. That boundary is the skin of the abyss, and it is a boundary defined by radiative escape. It is the last level where light escapes easily, and it is the first level where our certainty collapses, because the atmosphere turns opaque and our tools lose leverage. The skin is not calm or uniform even when the disk looks smooth at low resolution. It is shredded by shear, punctured by updrafts, and smoothed by subsidence, motions that sculpt brightness into bands and spots under a sky with almost no sun. If we could descend through that skin, the light would dim quickly, and the blue would fade into grey. The clouds would become thicker, the air heavier, and the concept of down would become a plunge into pressure rather than a descent toward ground. Remote sensing lets us read that skin like a medical scan, and the analogy is imperfect but useful. It can show temperature contrasts, trace gases and cloud heights, but it cannot reveal the full anatomy, and it cannot guarantee a single interpretation. This is why Neptune remains both familiar and unknowable, a world we can describe yet cannot inhabit. We can name its molecules and map its storms, yet we cannot watch the engine directly, and that gap is where the ore lives. The chapter's tension is therefore structural, and it grows as our measurements improve. The more precisely we describe the blue clouds, the clearer it becomes that they are only a boundary, and that the real planet begins where our light stops. Neptune's visible atmosphere is a thin interface between space and a deep interior, and it is always moving. That interior likely holds supercritical fluids, exotic ices, and chemistry under crushing pressure, and it sets the conditions that the clouds merely advertise. We are not there yet, but the logic points downward, and it points with insistence. If sunlight is too weak, then the driver must be internal, and the visible clouds are only its exhaust, venting energy into the cold. One sentence must carry us into the next descent, because the narrative is a fall through layers of inference. The blue mirage is not the planet, it is the mask that forces us to ask what powers the storm beneath, and what kind of heat survives so far from the sun. In the next chapter, we follow the energy, and we follow it with different eyes. We move from what Neptune reflects to what Neptune emits, and we trace the hidden heat that makes the abyss move. Neptune looks calm in reflected light, yet its atmosphere moves like a weaponized fluid under tension. The central question tightens here, because the planet is cold and dim, yet it accelerates air to the solar system's fastest winds. From a distance, the disk is a polished blue coin, edged by faint haze and thin, high clouds. Up close, that serenity fractures into streaks, scallops, and bright knots that slide across latitude bands with unsettling speed. The visuals invite a simple assumption: gentle weather on a distant world, but the physics refuses it. The headline numbers are not subtle, and they are not rare outliers. Cloud-top winds are often measured around 1,500–2,000 km per hour, which is fast enough to circle Earth in a single day. Some estimates push higher in brief regions, but the robust point is sustained, planet-scale speed that persists across seasons. It matters that these are not just gusts near a storm wall. On Neptune, entire jet streams appear to run like conveyor belts around the globe, and the fastest values show up repeatedly where contrast is sharpest. The planet is telling us that its atmosphere is organised, not merely agitated. We begin with how we know, because Neptune does not let us touch the air. No weather balloon has ever risen through its methane clouds, and no probe has sampled its winds directly. Everything we claim is built from light, timing, and carefully constrained inference. The simplest method is cloud tracking across time-lapse images, and it works because Neptune paints its own traces. We watch bright methane clouds shift in longitude over hours and days, then convert those drift rates into meters per second. When the cadence is good, the motion is unmistakable. Features slide like beads on invisible wires. Voyager 2 provided the first close, fast cadence for this technique, and it changed the story overnight. In 1989, as the spacecraft swept past, it captured sequences where clouds visibly march between frames, making the winds feel immediate. Later, Hubble and large ground telescopes extended the record, with adaptive optics sharpening features that would otherwise blur away into a uniform blue. There is history embedded in that progress because Neptune was once a planet of hints and smudges. Before Voyager, observers could suspect bands and storms, but the details were fragile and the timescales were hard to pin down. After Voyager, Neptune became a world with meteorology, measurable, repeatable, and surprisingly violent. Cloud tracking is powerful, but it's not a direct anemometer reading, and the caveats are real. Clouds are tracers that can form, fade, and change altitude while we measure, especially when convection pulses upward. A feature can also be a wave pattern, not a parcel of air, which means the pattern speed can differ from the bulk flow. Even the geometry complicates the measurement, because Neptune is a small target at extreme distance. We must correct for viewing angle, planet rotation, and the fact that high-latitude features project differently than equatorial ones. The best studies treat these corrections with care, and they still carry uncertainties that cannot be wished away. That uncertainty does not erase the result, because many independent tracers agree on extreme speeds. Different latitudes show consistent jet directions over decades of observation, which is hard to fake with transient clouds alone. The fastest values cluster where contrast is strongest, and tracking is clearest, and those clusters recur in the same dynamical neighbourhoods. A second tool is Doppler spectroscopy, which measures motion through shifted wavelengths and does not rely on visible cloud shapes. If gas moves toward us, spectral lines shift slightly blue, and if it moves away, they shift red. By measuring the size of that shift, we estimate line-of-sight wind, then reconstruct the broader flow with models and geometry. Doppler work is difficult at Neptune's distance, because signals are faint and lines are broadened by temperature and pressure. The telescope must separate Neptune's light from Earth's atmosphere, and it must do so with stable calibration over long exposures. It also samples specific altitudes tied to where the measured lines form, so it is a vertical slice rather than a full column. Still, Doppler measurements provide an important cross-check on cloud-derived winds, because they are sensitive to the gas itself. When both methods point toward the same extreme speeds, the conclusion hardens. The numbers stop being a dramatic claim and become a constraint that theory must respect. A third constraint comes from temperature itself, through the thermal-wind relationship, which links heat patterns to wind shear. Horizontal temperature gradients imply vertical changes in wind speed, because pressure surfaces tilt in a rotating atmosphere. By mapping temperatures, especially in infrared wavelengths, we infer how winds vary with height even when clouds are sparse. Thermal wind does not give absolute speed without a reference level, and that limitation is fundamental. It does tell us which latitudes should strengthen with altitude and where shear must exist to satisfy balance. Neptune shows strong shear signatures that match its banded circulation, suggesting that the jets are layered, not uniform slabs. So the measurement story is layered, like the atmosphere we are trying to decode, and each layer adds confidence. Cloud tracking gives fast, visible motion at specific cloud levels, often near methane condensation altitudes. Doppler adds direct velocity along our line of sight, and thermal wind ties temperature patterns to vertical structure that clouds alone cannot reveal. Even with these tools, error bars remain honest and unavoidable, and they shape how we speak about extremes. We do not always know the exact altitude of each tracked cloud, and altitude matters because wind speed can change with height. We do not know whether some features ride above the mean flow, yet the extreme winds persist across methods and epochs. The phrase supersonic enters here, and it needs careful handling because it is easy to oversell. The speed of sound is not a universal constant stamped across a planet. It depends on temperature, molecular weight, and the gas's heat capacity, which together determine how quickly pressure waves travel. Neptune's upper atmosphere is cold, near tens of Kelvin, which lowers the sound speed by reducing thermal motion. Its air is mostly hydrogen and helium, which raises the sound speed compared with heavier gases like nitrogen or carbon dioxide. The result varies with altitude and composition, and it can shift as methane and other trace species change with height. So, supersonic is contextual, not a single Mach number that covers the entire sky. At some levels, 2,000 km per hour could exceed the local sound speed, especially where temperatures plunge. At other levels, it could be near it or below it, depending on the thermal profile and the mixture. The useful idea is not a precise Mach claim, and it is not a headline designed to shock. The useful idea is that Neptune's winds approach the regime where compressibility matters, at least locally, and that changes the character of waves and turbulence. That is extraordinary for a planet with so little sunlight to spend, and it forces us to ask where the energy comes from. Now we ask what organizes such speed into coherent patterns, instead of letting it dissolve into chaos. Neptune rotates in about 16 hours, fast enough to strengthen the Coriolis effect and to dominate large-scale motion. In a rotating fluid, motion is deflected sideways, and large flows become curved and banded rather than simply rushing from warm to cold. Coriolis does not create energy, but it shapes how energy becomes wind, and it shapes what winds can persist. It favors jets that run east and west, because those flows can balance pressure gradients over long distances. It also helps storms spin up into long-lived vortices, where rotation becomes a stabilizing scaffold. Neptune's atmosphere shows broad zonal jets, alternating in direction with latitude, like lanes on a planetary racetrack. Near the equator, winds are often retrograde relative to the interior rotation, which means the atmosphere there lags behind the planet's spin. At mid-latitudes, prograde jets can dominate, with sharp shear between bands that act like invisible walls. These jets are not painted stripes, but dynamical structures maintained by momentum transport and by the way turbulence behaves on a rotating sphere. Eddies and storms can move momentum up gradient, sharpening jets rather than smoothing them, which is counterintuitive if you're trained on everyday friction. Rapid rotation makes that self-organization easier, because it constrains motion into quasi-horizontal layers. Pressure gradients are the immediate accelerators, and they are the local reason air speeds up. Air moves from higher pressure toward lower pressure, but on a fast-rotating planet it rarely goes straight for long. The flow turns until pressure gradient force balances Coriolis, producing near-geostrophic winds that can be extremely fast without being directly driven by surface friction. This balance explains why strong winds can exist without enormous day-to-night temperature differences, which would be the obvious driver on a tidally locked world. The atmosphere can store large horizontal pressure contrasts, then express them as fast, curved flow that wraps around the planet. The jets become highways for energy and momentum, and storms become the on-ramps and off-ramps. Vertical wind shear adds another layer of danger and complexity because Neptune is not a single moving sheet. If wind speed changes rapidly with height, clouds can stretch into streaks, and waves can steepen and break. Shear can also feed instabilities that spawn storms, and then storms feed back into the jets by redistributing heat and momentum. Neptune's bright cloud features often appear near jet boundaries, where shear is strongest and where the atmosphere is most likely to lift. That is where rising motion can trigger methane condensation, making traces visible as brilliant white patches against deep blue. It is also where turbulence can transfer momentum between layers, tightening the jets like a drawn bowstring. Storms complicate the picture because they are both products and engines, and Neptune seems to produce them in cycles. A large vortex can tap the background shear and convert it into rotation, maintaining itself like a spinning top in a moving stream. It can also alter the local temperature field, changing pressure patterns and reinforcing jets nearby, an atmospheric feedback loop. The Great Dark Spot was our first clear example, and it remains one of the most haunting images from Voyager's flyby. It looked like a bruise in the atmosphere, edged by bright companion clouds that rose and condensed in its wake. Later observations found new dark vortices that appear and vanish over years, suggesting that Neptune's storms are recurring structures rather than one-time anomalies. Their lifetimes hint at a balance between energy input, radiative cooling, and mixing, and that balance is difficult to maintain in a thin upper layer. If a vortex lasts for years, it must continually resist diffusion and the shredding effects of shear. That persistence implies that the atmosphere has access to a steady energy source, or to a structure that shelters storms from rapid decay. At this point, the mystery becomes sharper, because the usual driver is weak and the numbers are unforgiving. Solar heating at Neptune is tiny, about 1/900th of Earth's, because the sun is so distant and the light is so diluted. Sunlight can still shape the stratosphere and haze chemistry, and it can modulate temperatures, but it struggles to power global winds of this magnitude. Neptune's internal heat is the obvious alternative, and it is not subtle once you look at the energy budget. The planet emits roughly 2 to 3 times the energy it absorbs from the sun, which means it is glowing from within. That surplus must come from gravitational contraction, residual formation heat, or slow interior processes that release energy over billions of years. Internal heat can drive convection, and convection is a wind factory because it converts thermal buoyancy into motion. Warm, buoyant fluid rises, cools as it expands, and then sinks again, turning heat into kinetic energy. In a rotating planet, that motion tends to align into columns and bands, feeding jets rather than dispersing randomly. Convection also transports momentum upward, but not in a simple straight line that would be easy to model. Rising plumes can generate gravity waves and planetary waves that propagate and break as they encounter changing density and wind shear. When waves break, they deposit momentum, accelerating or decelerating the mean flow, and they can do so preferentially at certain latitudes. This is how a deep engine can influence a thin, visible layer, even when the sunlight is weak. Heat rises from below, launches waves, and reshapes the pressure field, and the atmosphere responds by reorganizing its jets. The cloud tops respond with fast winds that look disconnected from sunlight, because Neptune is spending internal energy on weather. Yet internal heat alone is not a complete explanation, because it must be converted efficiently into organized high-speed flow. Neptune's winds are faster than those on Jupiter in some regions, despite Jupiter's much larger heat flow and more obvious convective activity. The conversion mechanism must be unusually effective, or unusually unconstrained by drag, or both. One idea is that Neptune's atmosphere has low frictional drag at the levels we observe, allowing winds to build and persist once accelerated. If drag is weak, the jets can retain momentum for long periods, and storms can reinforce them rather than dissipate them. Another idea is that methane condensation and latent heat sharpen temperature gradients, strengthening jets by intensifying pressure contrasts where clouds form. Latent heat sounds abstract, but the plain language version is simple. When methane condenses, it releases energy into the surrounding air. That release can enhance buoyancy, drive stronger updrafts, and create sharper thermal boundaries that the Coriolis effect then organizes into jets. On a cold planet, even small compositional processes can have outsized dynamical consequences. But each explanation runs into limits as we push deeper, because the atmosphere is not just a surface skin. If the winds are only a shallow weather layer, then a thin mass of gas is moving very fast, which is easier to accelerate. That shallow layer must be continuously maintained against radiative damping, because the upper atmosphere can cool efficiently to space. If the winds extend deep, then an enormous mass is moving fast, carrying huge kinetic energy that must be supplied and sustained. That is harder to accelerate, because deep layers have inertia and may interact with interior structure. Yet deep winds could be more stable over time, because they are less exposed to rapid radiative losses and may be anchored by deep convection. The question becomes not just meteorology, but planetary interior dynamics, and that is where Neptune becomes elusive. The visible clouds are only the top of a vast fluid envelope, where pressure climbs quickly and the chemistry changes. When we ask how deep the winds go, we're also asking how the planet moves as a whole. So we ask the key depth question directly, and we let it hang in the cold air. How deep do Neptune's winds go? And what do they couple to below the cloud decks? Do they fade beneath the methane layer, or do they penetrate into the dense fluid envelope where hydrogen behaves differently? Competing models split along that boundary, and the split is not cosmetic. Shallow flow models place the jets in the upper few hundred kilometers, driven by atmospheric turbulence, wave forcing, and radiative contrasts. Deep flow models link jets to convection throughout much of the outer envelope, like a global dynamo of motion that reaches far below the visible clouds. Both can reproduce parts of what we see, and both struggle with something important that keeps the debate alive. Shallow models must explain how such extreme speeds persist, with limited solar forcing and with radiative cooling that should sap energy. Deep models must explain how deep winds avoid being damped by electrical conductivity and magnetic drag as pressure rises. Magnetic fields enter the wind story because moving conductive fluid feels Lorentz forces, and those forces resist motion like an invisible brake. If deep layers conduct electricity, fast flow can induce currents that push back against the wind. That magnetic braking could limit wind depth or reshape it into different patterns, and it could do so without leaving obvious surface clues. Gravity also becomes a wind detector, because moving mass changes a planet's gravity field in subtle but measurable ways. If jets extend deep, they shift mass laterally and create gravitational anomalies that an orbiter can map. With enough precision, those anomalies can reveal how far the winds penetrate, because shallow winds and deep winds produce different signatures. Neptune has not had that kind of orbital gravity mapping, and the absence is a major reason the mystery persists. Voyager's flyby gave only limited gravity harmonics, insufficient to separate deep winds from static interior structure. So the depth question remains open, and it remains central, because it decides whether Neptune's weather is skin deep or planet deep. We can still build indirect constraints from rotation and shape, and those constraints are suggestive even when they are not decisive. Neptune's oblateness reflects its internal rotation and density distribution, because a spinning fluid planet bulges at the equator. If winds carry significant angular momentum deep down, they can slightly alter the inferred rotation profile, shifting how we interpret the planet's shape. But Neptune's true internal rotation is itself uncertain, because we measure it through magnetic periodicity rather than a solid surface. If the magnetic field is generated in an offset tilted shell, its period may not match the deep interior's rotation. That uncertainty leaks into every wind model, because rotation sets the scale for Coriolis balance and jet formation. So the deeper we look, the less conventional explanations suffice, and the more the unknowns begin to dominate. We can describe geostrophic balance, pressure gradients, and Coriolis organization, and the math behaves with elegant restraint. We can point to internal heat as the fuel, and the energy budget agrees, yet the conversion details remain stubbornly out of reach. Then we hit the wall of missing information, and it is not a small wall. We do not know the drag regime at depth, where pressure and composition change the fluid's behavior. We do not know the conductivity profile through the ice-rich mantle, and we do not know whether stable layers block convection or whether convection punches through in episodic bursts. Neptune's fastest winds therefore become a diagnostic, not just a spectacle for a highlight reel. They are evidence that heat, rotation, and composition are coupled in a way we do not yet capture with confidence. They are also a warning that our intuition, trained on Earth's sunlight-driven weather, is underpowered here. Neptune runs on a different budget. We return to the opening hook, because the scream is the clue and the contradiction is the point. Nearly 3 billion miles from the sun, Neptune should whisper, conserving energy in the cold. Instead, it screams through winds that may rival sound in certain layers, and it keeps screaming without sunlight to pay the bill. The chapter ends with a boundary we cannot cross from Earth, no matter how sharp our telescopes become. To know whether the winds are shallow or deep, we need gravity and magnetic constraints measured over time, not just snapshots. We need an orbiter that can watch storms evolve, map fields precisely, and separate weather from interior with repeated passes. Until then, Neptune's supersonic reputation remains both true and incomplete, a fact and a provocation. The measured winds are real, extreme, and organised by rapid rotation, and they demand a deep energy source. The deeper cause is still hidden, and the abyss keeps its fastest secret, just out of reach, but not out of mind. Next, we follow the consequences of that hidden engine. If Neptune can drive winds like this, it can also transform matter below, where pressure rewrites chemistry and familiar materials become strangers. The scream at the cloud tops may be the echo of diamonds forming in the dark. Neptune's winds already sound impossible, but the storms make the claim personal. Suddenly, the numbers have a face. In this sky, stability is temporary, and the atmosphere can rewrite itself within a few years. The planet looks serene from afar, a smooth blue bead at the edge of sunlight, yet that calm is a thin skin over relentless motion. Voyager 2 arrived in 1989 after a 12-year journey, and it found a wound in the blue. It was the Great Dark Spot, a vast oval storm in Neptune's southern hemisphere, set against bands that looked almost painted. Its scale rivaled Earth, and its presence proved Neptune's weather was not slow. The images carried a shock of clarity, an organised system on a world once thought too distant, too cold, and too quiet for such drama. The Great Dark Spot was not a hole, and it was not a gap to deeper layers. It was a vortex, a rotating system that changed the cloud field and the chemistry above it. Dark meant reduced reflectivity, not missing atmosphere, and that distinction matters because it changes what we think we are seeing. Instead of emptiness, the darkness points to structure, to circulation, and to a column of air being rearranged from top to bottom. Voyager saw structure, not a simple dark stain, and the geometry hinted at a living flow. The spot had a defined boundary, an interior with subtle gradients, and edges shaped by shear from surrounding winds. Along one side, bright companion clouds flashed like signals tied to the vortex circulation. In the best frames, the storm looks like an eye without a pupil, an oval of altered brightness, surrounded by streaks that reveal the wind's grip. Those bright clouds were not decoration, and they were not separate storms drifting nearby by chance. They formed where air was forced upward, cooled rapidly, and condensed methane into reflective ice. They traced uplift at the vortex margins and in its wake, like foam tracing a hidden current. Each bright patch is a momentary marker of vertical motion, a reminder that even in a hydrogen-dominated atmosphere, weather is still built from rising and sinking air. Scale matters because it sets the physics regime, and Neptune's storms live in a different category than most terrestrial intuition. On Earth, hurricanes feed on warm oceans and die over land or cold water, limited by friction and geography. On Neptune, there is no surface ocean, yet the storm reaches planetary dimensions. The energy source is not a sunlit sea, so the storm's very existence forces a deeper explanation. To understand why, we treat Neptune's atmosphere as a rotating fluid, not a weather map. Rotation organises chaos into coherent structures, especially when friction is weak and the ground is thousands of kilometres below the visible clouds. The planet's rapid spin makes large vortices dynamically favoured, because the Coriolis effect becomes a dominant actor rather than a minor correction. When rotation is strong, the flow prefers wide, stable patterns over small, quickly shredded swirls. A vortex is defined by vorticity, the measure of local spin in a flow, and it is one of the cleanest ways to describe storm identity. When vorticity concentrates, it can become a stable structure that resists mixing with its surroundings. In rotating fluids, turbulence often self-organises into jets and long-lived eddies, a behaviour seen in laboratory tanks and in numerical models. Neptune is like an immense experiment, one where the walls are invisible and the fluid is a layered mix of hydrogen, helium, and trace gases. Neptune's dark spots are generally interpreted as anticyclones, and that label carries specific dynamical meaning. Anticyclones rotate opposite the local planetary vorticity sign and often correspond to high-pressure systems, where air tends to sink at the centre. They can be dynamically stable, especially at certain latitudes where the background flow supports them. On a giant planet, high pressure does not mean a rigid surface reading, but a three-dimensional balance across layers of gas. Cyclones are the other branch, And they matter for contrast because they behave differently in a stratified atmosphere. Cyclones rotate the other way and tend to be associated with low pressure and rising motion, which can build clouds rather than suppress them. On Neptune, both types can exist, but the famous dark ovals fit anticyclonic behaviour. That is one reason darkness is such a clue, because sinking motion can erase bright haze and change what altitude we're seeing. The key is how pressure, rotation, and shear balance, and the simplest description is geostrophic flow. In geostrophic flow, pressure gradients are balanced by Coriolis deflection, so winds run along isobars instead of rushing directly downhill. That balance allows fast winds to wrap around a vortex without immediately collapsing into the centre. It also means the storm's shape can be maintained by invisible bookkeeping, forces that cancel so precisely that the vortex becomes a coherent object. Neptune's vortices also live inside a banded jet system, and those bands are not just visual stripes. Jets provide background shear that can stretch, feed, or shred storms depending on the alignment and strength of the flow. A vortex can draw energy from that shear, like a spinning wheel in a fast stream, extracting momentum from the surrounding wind field. The same shear that sharpens a boundary can also become the blade that eventually cuts the storm apart. The Great Dark Spot sat in a latitude zone where the surrounding winds differed strongly, and that contrast likely shaped its oval form. That shear helped sharpen its boundary, and it created regions where companion clouds could repeatedly form. In a sense, the storm was embedded in a conveyor belt of atmospheric motion, and the belt itself may have helped sustain the vortex. The oval is not arbitrary. It is the imprint of a rotating system negotiating with a moving background. Darkness in these spots is a physical signal, not a void, and several mechanisms can produce it. One idea is that the vortex drives subsidence in its core, warming and drying the column as it compresses. That suppresses high clouds and hazes, letting us see deeper and darker layers where methane absorption and reduced scattering change the tone. The darkness becomes a window not to empty space, but to different pressure levels. Another idea is aerosol chemistry, changed by circulation and isolation over time. If particles that normally scatter light are removed, altered, or coated, reflectivity drops even if the gas remains. A vortex can act like a chemical reactor by isolating air and changing exposure histories, including how long aerosols spend in sunlight or in regions rich in reactive species. The storm is then not only a dynamical structure, but a moving laboratory that edits the atmosphere's optics. The spot's colour and contrast depend on microphysics we cannot fully sample, and Neptune makes that uncertainty unavoidable. Particle size, composition, and altitude decide how much sunlight returns, and they also decide which wavelengths brighten or fade. Neptune forces us to infer those properties from spectra and brightness changes, using models that connect chemistry to scattering. Each image is therefore both a picture and a puzzle, an observation that must be translated into physics. Then the story turns, because Neptune's storms do not behave like monuments. The Great Dark Spot did not persist for decades like Jupiter's Great Red Spot, which has been tracked since at least the 19th century. When Hubble looked again in the 1990s, the original spot was gone. The disappearance felt abrupt, as if the planet had simply erased a feature the size of Earth between visits. Its disappearance was not a measurement error, and it was not a slow fade into invisibility. Neptune's atmosphere had reorganized, and the vortex either dissipated or sank below the visible layers where methane clouds mark the weather. The planet replaced it with new dark spots later, sometimes in different hemispheres and latitudes. That replacement is important, because it suggests a recurring process rather than a single rare accident. This is the unsettling pattern, and it changes how we think about giant planet meteorology. Dark vortices appear, drift, change shape, and then vanish on timescales of years. That is fast for a giant planet, and it implies a delicate balance between formation and destruction. If a vortex can be Earth-sized yet short-lived, then the controlling forces must be both powerful and finely poised. One mechanism is vertical mixing that erodes the contrast, even if the circulation remains. If turbulence or convection injects aerosols back into the column, the dark signature can fill in from above. If mixing changes methane distribution, cloud formation patterns can also shift, and the bright traces we rely on may relocate. In that case, the storm might still exist dynamically, but the visible marker we call a spot could dissolve. Another mechanism is changing wind fields that destabilize the vortex, especially in a jet-dominated atmosphere. If the surrounding jets migrate, strengthen, or change curvature, shear can tear the vortex apart through instabilities at its boundary. A storm that is stable in one flow regime can be doomed in another, even if its internal rotation remains strong. Neptune's atmosphere may therefore act like a shifting set of rails, and the storm survives only while the rails align. Radiative effects may also matter, even in weak sunlight, because cooling controls stratification and wave behavior. Cooling rates vary with altitude and composition, and they can change the stability that separates layers. If stability changes, waves and turbulence can penetrate differently and disrupt a vortex from above or below. Neptune's dim illumination does not mean radiative physics is irrelevant. It means the timescales are different, and small imbalances can accumulate. Neptune's vortices may also be shallow features that depend on a narrow altitude window, like patterns drawn on a thin fog layer. If the visible cloud deck rises or falls, the storm's signature can detach from what we can see. The vortex might persist below while the dark spot disappears, leaving us with the illusion of death. That possibility forces caution, because telescopes track brightness, not vorticity. That possibility reframes the question in a way that is almost philosophical. Are we watching storms die, or are we watching the planet change which layers are visible? Neptune's atmosphere can hide its own dynamics by shifting cloud and haze levels. The same circulation that builds a vortex can also adjust the curtain we use to observe it. Storm life cycles begin with how vortices form in the first place, and formation is often an instability story. In a rotating, stratified atmosphere, instabilities can roll up into eddies when smooth flow becomes dynamically impossible. Barotropic instability feeds on horizontal shear, while baroclinic instability feeds on vertical shear and temperature gradients. Both mechanisms can convert organized jet energy into swirling structures, and both are sensitive to how temperature and wind vary with height. Once formed, a vortex must resist diffusion and wave breaking, which constantly try to smear it out. Turbulence tries to spread vorticity into the background, while jets can either confine it or stretch it into filaments. Longevity depends on energy supply, background shear, and how strongly layers are coupled across the atmosphere. If the vortex is deep, it may be harder to kill. If it is shallow, it may be easy to hide. Neptune storms also interact with waves that carry momentum, and those waves can reshape the environment. Gravity waves and planetary waves can be launched by convection or by flow over vortices, and they propagate until they dissipate. When those waves break, they deposit momentum and can accelerate or decelerate local winds. The atmosphere becomes a feedback machine, where storms create waves, and waves rewrite the conditions for storms. That feedback can help a vortex persist, or it can help it collapse, depending on where momentum is deposited. A storm can modify its environment until the environment no longer supports it, a kind of self-limiting behavior. Neptune's rapid changes suggest that such feedbacks are strong, and perhaps more efficient than on warmer, more heavily damped worlds. The planet's weather may be balanced on thresholds that are crossed more easily than we expect. Cloud microphysics anchors the visible drama to the hidden thermodynamics, and it explains why bright and dark features are so informative. At the cold upper levels, methane condenses into ice clouds that reflect sunlight efficiently, producing sharp white streaks and compact bright knots. Those clouds are the traces we track, and they respond quickly to vertical motion because condensation can occur in minutes to hours. When air rises, it cools, methane freezes, and the sky briefly writes down the motion in bright ink. Deeper down, other condensables should appear as pressure rises and temperature increases, building a layered cloud system. Ammonia is expected at intermediate depths, though its exact cloud level depends on mixing and chemistry that can shift the condensation point. Hydrogen sulfide compounds may also contribute to cloud decks, and they can alter color and opacity. Each layer changes how radiation moves upward, and that changes how quickly the atmosphere can cool. Deeper still, water becomes the major latent heat player, and its role is potentially transformative. Water clouds would form at much higher pressures and temperatures, far below the methane layer, in regions we cannot image directly. If water condensation occurs, it can release substantial energy and drive powerful convection, analogous to thunderstorms on Earth but operating under very different gravity and composition. In that deep darkness, buoyant plumes may rise for hundreds of kilometers before they slow. That matters because storm energy depends on buoyancy sources, and latent heat is one of the most efficient. On Earth, latent heat from water vapor is the hurricane's fuel, and it organizes winds into a heat engine. On Neptune, methane latent heat can energize shallow storms, while water latent heat could power deeper convective towers. The visible atmosphere may therefore be only the upper expression of a deeper, more energetic cycle. We cannot yet say how often deep water storms punch upward into the visible sky, because our observations are intermittent and our probes are absent. If they do, they could seed vortices, launch waves, and inject aerosols that change reflectivity across wide regions. The visible atmosphere could be the exhaust of deeper convection, vented upward and then sculpted by rotation. That idea makes each dark spot feel less like a surface blemish and more like a symptom of interior weather. Lightning is the unresolved question that tests these ideas because it's a direct signature of vigorous convection. Lightning requires charge separation, usually in turbulent convective clouds with mixed phases and frequent particle collisions. On Neptune, the best candidate would be deep water clouds, where strong updrafts can separate charges and build electric fields. If lightning exists, it would imply not just storms, but storms with violent vertical structure. Voyager detected radio emissions consistent with lightning on several giant planets, but Neptune's evidence is limited and ambiguous. The distance makes detection difficult, and the signal may be intermittent, buried in noise and competing radio sources. A lack of clear lightning does not mean a lack of deep storms, because the storms could be rare, localized, or simply hard to hear across billions of kilometers. The silence could be instrumental, not meteorological. If lightning exists, it would confirm energetic convection and strong vertical transport, tying the weather to deep thermodynamic processes. It would also imply complex cloud microphysics, including particle collisions, phase changes, and perhaps hail-like ice mixtures at high pressure. That would connect Neptune's atmosphere to the same fundamental electricity that crackles in Earth's thunderheads, even though the ingredients differ. The question becomes, how familiar can a storm be on an alien planet? Even without lightning, the storm signatures imply vertical motion and heat transport, and the companion clouds are the clearest evidence. Companion clouds indicate rapid uplift and cooling at vortex edges, where flow is forced upward by the rotating circulation. Their appearance and disappearance show that condensation responds on short timescales, and that the atmosphere is continually near a threshold. When the threshold is crossed, the sky brightens instantly, then fades as air sinks or warms. Neptune's dark spots also migrate, and that drift is diagnostic rather than incidental. Vortices move with background flow, but they also feel planetary beta drift, driven by latitude-dependent Coriolis strength. That drift can carry storms into regions where they become unstable, or into jets that stretch them into ribbons. A storm's path is therefore also a test of the planet's rotation, because the Coriolis parameter itself changes with latitude. So Neptune becomes a planet of recurring storms, not a planet with one famous storm frozen in time. Each new dark oval is a reminder that the atmosphere can assemble large vortices quickly, even in weak sunlight. Each disappearance is a reminder that the same atmosphere can erase them, either physically or optically. The planet behaves less like a museum exhibit and more like a living system that refuses to hold still. This is where the suspense belongs, because it is not just violence, it is unpredictability at planetary scale. The patterns look stable until they are not, and the changes can happen between our brief windows of observation. Neptune's weather is a system that can reorganize in years, not centuries, and that speed challenges the idea that distant giant planets are slow. The storm is a warning that remoteness does not guarantee calm. The Great Dark Spot was our first warning that Neptune's calm face is misleading, and the warning came in layers. Its structure showed coherent rotation, not a missing patch of cloud, and the oval boundary hinted at balanced forces. Its companion clouds showed active uplift, not passive shading, and they revealed the vortex as a machine that moves air vertically. Even the spot's darkness became a clue, pointing to subsidence, chemistry, or a deeper view. Its vanishing showed something even more disturbing, because it implied that the system can reset without leaving a clear trace. Neptune can destroy or hide an Earth-sized vortex without leaving a scar we can easily track. The planet can reset its visible atmosphere faster than our theories feel comfortable, especially when those theories were built on sparse data. The disappearance is not an ending, but a demand for better physics and better monitoring. How can a cold, dim planet sustain the fastest winds and build storms this large, and why do those storms come and go so quickly? The storms are not the engine, and they are not the answer, but they reveal the engine's fingerprints. They show us where energy is being organised, and they hint at where it is coming from. Storms are symptoms, and symptoms demand a cause. Vortices need energy, and the rapid turnover suggests a powerful driver beneath the cloud tops, one that can supply momentum and maintain sharp gradients. Sunlight is too weak to pay the bill at Neptune's distance, where the sun is a bright star rather than a warming lamp. If the atmosphere is spending energy so freely, something else must be funding the motion. So we pivot from weather to power, and the pivot changes the scale of the mystery. Neptune emits more energy than it absorbs, and that imbalance leaks upward into the atmosphere as a steady internal heat flux. Internal heat can steepen gradients, drive convection, and feed the vortices we see, even when the surface is only a cloud top. In the dim outer solar system, the planet is still warm from within, and that warmth can be dynamic. If storms can appear and vanish this quickly, the deep engine must be active and variable, not a fading ember. To understand the storms that should not exist, we have to follow the heat that should not be there. And once we follow that heat, we are no longer studying weather alone. We are studying the planet's hidden life. Neptune should be a cold endpoint, a world living on borrowed sunlight at the edge of the sun's reach. Yet it behaves like a generator, spending energy on winds, storms, and constant atmospheric motion that never seems to tire. In wide shots, the planet looks serene, a blue marble wrapped in pale bands and thin cloud streaks. Up close, that calm is a mask, because the air is racing and the weather is restless. The paradox is measurable, not poetic, and it starts with a simple budget that any engineer would recognize. Neptune absorbs weak solar energy, then radiates far more heat back into space than it receives. It is like a dimly lit object that still glows from within, because something inside stays warm. The farther you go from the sun, the more striking this becomes, since the sunlight is diluted across an ever larger sphere. At Neptune's distance, the solar flux is only a small fraction of what Earth receives, so the top of the atmosphere should be starved. The clouds are cold, the light is thin, and the days are long, and yet the planet's thermal signature says it is not merely coasting. We know this because Neptune shines in infrared, even when visible light is scarce and the disk looks muted. Telescopes compare incoming sunlight to outgoing thermal emission, then compute a surplus that cannot come from the sun. The method is straightforward in principle, but it demands careful calibration and years of repeated measurement. Instruments measure how bright Neptune appears at different wavelengths, including bands where methane absorbs and bands where heat leaks out. Those spectra carry temperature information, because warm objects emit more strongly in the infrared. When scientists integrate that emission over the whole planet, the numbers keep pointing to the same conclusion. The result is consistent across decades, even as clouds and storms rearrange the surface patterns. Weather changes what we see, but it does not erase the underlying heat flow. Neptune's atmosphere is dynamic, yet the internal glow remains stubbornly persistent. This is the hidden furnace behind the scream of the winds. The fastest jets and transient dark spots are not just weather curiosities. They are the exhaust of an interior that never fully cooled, venting energy through an atmosphere that turns heat into motion. To explain the furnace, we start with what is known and what is inferred, because the line matters. Known is the imbalance between absorbed and emitted energy, which is measured rather than guessed. Known is Neptune's size, mass, density, and broad atmospheric composition from spectroscopy, occultations, and gravity. From those measurements, we can estimate how much material is inside and how it must be arranged in bulk. We can also constrain temperatures in the upper atmosphere, where sunlight and radiation compete. Inferred is the detailed interior layering, the efficiency of heat transport, and the exact path from deep heat to cloud-top motion. The first candidate heat source is primordial heat, left over from formation in the early solar system. When Neptune assembled, impacts and compression heated the growing planet, and that energy was stored in deep, high-pressure material. Much of that heat should have escaped over billions of years, yet some can remain trapped if the interior cools slowly. The idea has a historical backbone, because planetary scientists have long treated giant planets as cooling embers. Jupiter and Saturn also radiate more than they receive, and that fact shaped early theories of their interiors. Neptune joins that family, even though it is smaller and far more distant. Slow cooling is not a handwave, it is a transport problem with physical bottlenecks. Heat must move upward through dense fluid layers, then radiate away at the top where space can carry it off. If the interior resists convection, or conducts heat poorly, the planet can stay warm long after formation. In everyday terms, convection is the churning that happens when warm fluid rises and cool fluid sinks. In a pot of water, it is obvious, because bubbles and swirls appear quickly. In Neptune, convection happens under pressures so extreme that the fluid's behavior changes, and the churning can be slowed or reshaped. Neptune's interior is not a simple gas ball with a neat boundary between air and ground. Pressure rises fast and the material changes phase and behavior with depth. Hydrogen becomes a dense fluid, and the so-called ice components become hot, compressed mixtures rather than familiar solids. That word ice is a legacy term from planetary science, meaning volatile compounds like water, ammonia, and methane. In Neptune's mantle, those substances are not frozen, and they do not behave like household liquids either. They are squeezed into exotic states where chemistry, conductivity, and density can shift with small changes in depth. That composition matters because it controls how easily heat can rise. A layered interior can act like insulation, where stable density gradients suppress overturning. If convection is throttled, heat leaks upward slowly, and the planet remains internally bright even while its cloud tops stay frigid. One way to picture this is to imagine warm fluid trapped beneath a heavier, slightly different mixture. Even if the lower layer is hotter, it may not rise because it is still denser. The result is a planet that stores heat like a thermos, releasing it in a controlled leak rather than a rapid flush. A second candidate is differentiation, the slow rearrangement of material by density under gravity. Heavy components tend to sink, and lighter components tend to rise, releasing gravitational potential energy as heat. This is not necessarily a one-time event, because mixing and chemistry can keep evolving under pressure. Differentiation is familiar on rocky worlds, where iron sinks to form a core and lighter silicates form a mantle. In an ice giant, the ingredients are different, but the principle is the same. When materials separate, they fall inward, and that falling releases energy that becomes internal warmth. Differentiation can also create compositional layering that changes the cooling rate. If layers form that resist mixing, they can trap heat below. The planet then radiates a steady surplus, not because it is generating new heat rapidly, but because it is losing old heat reluctantly. A third candidate is gravitational contraction, the Kelvin-Helmholtz mechanism that links slow shrinkage to heating. A planet can contract by a tiny amount over time, and that slow contraction converts gravitational energy into thermal energy. The change in radius can be small, yet the energy released can be large on planetary scales. Kelvin and Helmholtz developed the basic idea in the 19th century, long before spacecraft, as a way to explain how luminous bodies could shine without burning fuel. For planets, the mechanism is gentler than for stars, but it is still powerful. Neptune does not need to collapse dramatically to make a meaningful heat contribution. Kelvin-Helmholtz heating is easiest to picture as tightening a spring inside a heavy machine. As the planet settles inward under its own gravity, pressure rises and the interior warms. The planet glows because it is still relaxing from its birth, still paying off the energy debt of assembly. None of these sources require nuclear reactions or exotic physics hidden behind the clouds. They require time, insulation, and the ability of a massive fluid world to store heat. Neptune is cold at its cloud tops, but it is not thermally dead, and the evidence is written in its infrared light. The story sharpens when we compare Neptune to Uranus, its near twin in size and composition. Uranus also formed in the outer solar system, and it should have similar primordial heat stored inside. Yet Uranus emits only a little more than it receives, and its internal heat flux is weak. On a chart, the contrast is stark because the planets sit side by side in mass and radius. In images, they can even look like siblings, tinted by methane and wrapped in hydrogen and helium. But in thermal emission, Uranus is subdued, while Neptune is bright enough to demand an explanation. This difference is one of the most important clues in giant planet science, because it breaks the simplest expectations. Two planets with similar masses and similar atmospheres should not diverge so strongly in internal brightness. If Neptune is a furnace, Uranus is a banked ember, and the contrast demands explanation. One hypothesis is impact history, where a giant collision altered Uranus's interior early on. A major impact could have tipped Uranus on its side, then left behind a stratified interior that suppresses convection. If heat cannot rise efficiently, the planet looks colder from space even if energy remains trapped below. The idea fits the visual fact of Uranus's extreme axial tilt, which is difficult to produce gently. A violent event could also stir the interior, then allow it to settle into layers that do not mix easily. In that scenario, Uranus becomes a planet with heat locked behind an internal barrier. Another hypothesis is inhibited convection from compositional layering, even without a single catastrophic impact. If Uranus developed a stable gradient in composition, buoyant parcels cannot rise easily, and the interior becomes thermally isolated. The planet then cools from the outside in, while deep heat stays locked away. A related idea is that Uranus and Neptune differ in how their interiors mix over time, even if they started similarly. Neptune may have avoided long-lived stable layers, allowing convection to carry heat upward in a more continuous pipeline. Uranus may have built barriers that act like insulation, turning its interior into a sealed container. There is no single accepted answer, and the uncertainty is part of the tension that drives new missions. We can measure the heat flux at the top, but we cannot yet map the full internal structure with precision. We infer layering from density, rotation, and magnetic fields, then test models against limited constraints. Neptune's magnetic field hints at complexity rather than a simple, deep dynamo like Earth's. It is tilted and offset, suggesting that electrically conducting fluids exist in a shell, not a central core. That same shell structure could influence heat transport, and it could help explain why Neptune's interior remains active. Magnetism is not just a compass curiosity, because it implies moving, conducting material at depth. Conductivity rises when pressure forces electrons into more mobile states, and when temperatures keep fluids from freezing into rigid lattices. A dynamo needs motion, and motion needs energy. So the field becomes another sign of an interior that refuses to go quiet. The furnace is not just a number on a chart, it is a driver of motion that shapes what we see. Internal heat creates buoyancy, and buoyancy drives convection, even when sunlight is too weak to do the job. Warm material rises, cool material sinks, and the planet turns heat into circulation. On a rapidly rotating world, convection does not rise as random bubbles in a featureless sky. Rotation organizes flow into columns and bands, aligning motion with the spin axis through the Coriolis effect. Those convective columns can feed jets, reinforce shear, and seed the vortices that become dark spots. In visual terms, imagine the atmosphere as a spinning drum filled with fluid, where rising plumes are twisted into long structures. Instead of a single thunderhead, you get organized lanes of motion that can persist. The planet's rotation acts like a sculptor, carving raw convection into coherent patterns. This is how the energy budget connects to the weather we already saw. The storms are not powered mainly by sunlight, because sunlight is too weak at 30 astronomical units. The storms are powered by internal heat that reaches the atmosphere, then gets shaped into organized wind by rotation. Convection also launches waves that carry momentum upward through the stratified layers. Gravity waves and planetary waves can propagate, break, and deposit momentum into the mean flow. That deposition can accelerate jets, helping explain why Neptune's winds can reach extreme speeds. When those waves break, they behave like surf collapsing on a beach, except the beach is an invisible layer of gas. Energy and momentum are transferred, and the background winds adjust in response. Over time, this invisible bookkeeping can build jets that are faster than intuition expects. The conversion is not perfectly understood, and we should not pretend it is settled. We know internal heat is available, and we know the atmosphere responds with vigorous dynamics that exceed solar forcing. We infer the pathways through models that reproduce jets and vortices, but the details depend on unknown drag and unknown vertical coupling. Drag is a deceptively simple word, because in a giant planet it can come from many places. It can arise from turbulence, from wave breaking, and from interactions with deeper, denser layers. Each option changes how efficiently the atmosphere can turn heat into long-lived wind. This returns us to the depth question from earlier chapters, because depth controls the planet's inertia. If the winds are shallow, the furnace mainly agitates a thin layer that radiates quickly. If the winds are deep, the furnace is coupled to a much larger mass, and the planet's entire envelope participates. Deep winds raise another constraint, because conductivity increases with pressure in Neptune's interior. Conducting fluids moving through magnetic fields experience magnetic drag, which can break motion and convert kinetic energy back into heat. That breaking could limit how deep fast winds can penetrate, and it could differ between Uranus and Neptune. This is one reason magnetic measurements matter beyond the field itself. If we know where the dynamo operates, we can estimate where conductivity becomes significant. Then we can ask how far the jets can plausibly extend before magnetic drag becomes too costly. Without an orbiter, these remain competing possibilities rather than settled facts. We lack long-term gravity mapping that could reveal mass shifts from deep jets and differential rotation. We lack repeated magnetic measurements that could separate interior rotation, dynamo region, and atmospheric coupling. A single flyby gives a snapshot, and snapshots can mislead when a planet changes on seasonal and storm timescales. Neptune's year is long, and its atmosphere can evolve in ways we only partly capture from Earth. The furnace, however, is slow, and that steadiness is one of its signatures. Still, the broad narrative is clear enough to build on because the energy accounting is unforgiving. Neptune radiates more than it receives, and that surplus is persistent across methods and epochs. The simplest explanation is stored and slowly released energy from formation and ongoing gravitational settling. The furnace also explains why Neptune can look calm and still be violent when you measure the winds. A planet can have cold cloud tops and still have a warm interior, driving buoyant motion below. The visible sky is a thin boundary layer, and the real engine sits far beneath the methane haze. Neptune's heat is also a kind of memory, a record of how it formed and how it evolved through deep time. Every watt it emits is a piece of ancient energy escaping after billions of years of confinement. The planet is still burning its birth into space, even in near darkness. That thought invites a question that feels almost philosophical, but it is also scientific. How long can a world hold on to its beginnings, and what does it take to erase that imprint? Neptune suggests that in the outer solar system, time moves differently because cooling is slow and interiors stay active. We can now state what we can confidently claim, and we can separate it from what remains model-dependent. Neptune's internal heat flux is strong compared to its absorbed sunlight, and the imbalance is not subtle. That heat is sufficient to drive convection that can power weather and sustain jets over long intervals. The exact mixture of primordial heat, contraction, and differentiation is uncertain, but the need for an internal source is not. The planet's infrared glow is the receipt, and the winds are the visible spending. Whatever the interior is doing, it is paying for motion at the top. We can also state what remains inferred and contested because these are the open doors. We do not know the interior's detailed layering, or how efficiently heat crosses boundaries between compositionally distinct regions. We do not know how deep the winds run, or how magnetic drag reshapes flow at depth. We do not know why Uranus is so much quieter, though impact history and inhibited convection remain leading ideas. The two planets form a natural experiment, and nature has withheld the full answer. That is why Neptune's furnace is not only a feature, but a clue. The furnace is therefore both an answer and a doorway, which is what makes it compelling. It answers how a dim planet can afford such violent motion year after year without sunlight as the primary fuel. It opens the deeper question of what the interior is made of and what heat does to matter under crushing pressure. To understand the furnace, we have to descend. Past the methane clouds and the visible weather, the word ice stops meaning frozen water. In Neptune's mantle, ice becomes hot fluid mixtures, exotic phases, and chemistry that behaves like a different element. As the camera drops through the haze, the blue light fades, and the world becomes a gradient of pressure. Layers compress, temperatures climb, and familiar boundaries dissolve. The descent is not toward a surface, but toward regimes where matter is forced into new rules. The next chapter follows that descent because heat is not only energy, and it is not only a number in a budget. Heat is a sculptor that changes materials, separates components, and builds strange oceans in the deep. If Neptune's winds are the scream, then the mantle is the throat that makes it possible. We leave the cloud tops with one final constraint, and it is the chapter's spine. Neptune is not merely reflecting sunlight at the solar system's edge, faint and passive in the cold. Neptune is shining from within, and the glow is strong enough to drive a world that never stopped moving. Neptune's winds scream at the cloud tops, but the power budget points downward, into a planet that refuses to cool quietly. The planet radiates more heat than sunlight can supply, so the engine must live inside, hidden beneath the blue. To understand the furnace, we have to descend past the blue illusion. The colour belongs to a thin corridor of atmosphere, not to any surface, and that distinction matters as we imagine the fall. Above, sunlight scatters through haze and cloud, and the planet looks calm from a distance. Below, the same light is absorbed, and the world becomes a pressure-driven machine. Neptune is called an ice giant, and the name is a trap for intuition, because it smuggles in the wrong picture. In planetary science, ice means volatile compounds, not frozen cubes, and the term is historical rather than literal. Water, ammonia, and methane are counted as ices, even when they are hot, dense, and chemically restless. That language grew out of formation theory, when scientists realized the outer solar system was built from materials that condense at low temperatures. Far from the sun, water and other volatiles could freeze early, and those solids helped planets grow quickly. Neptune still carries that inventory, but gravity and time have rewritten the phase of almost everything. The descent begins in the outer envelope, dominated by hydrogen and helium, the light gases that set the planet's size. At the top, pressures are measured in fractions of a bar, where clouds can form and vanish quickly in fast winds. Methane absorbs red light, leaving blue behind, and high clouds paint bright streaks across darker layers. A few tens of kilometers down, the gas thickens and light is swallowed, as if the sky itself were turning to ink. The temperature rises, and the air becomes a fluid with weight, pressing from every direction. Sound would travel differently here, and turbulence would feel less like wind and more like a moving ocean of gas. Pressure is the first rule of the interior, and it rises relentlessly with depth, because every layer must support the mass above it. Each additional kilometre adds weight, and weight becomes compression, squeezing molecules into closer contact. Compression changes density, chemistry, and the way heat moves, so the interior is not just deeper, it is different. Temperature is the second rule, climbing from frigid cloud tops to thousands of Kelvin below, even though the sun is distant and weak. Neptune's internal heat keeps the deep layers warm despite the dim sun, and that warmth is not a surface feature. The deeper we go, the less the planet resembles a cold world, and the more it resembles a slow-burning engine. Where does that heat come from, if sunlight cannot pay the bill? Part of it is leftover energy from formation, trapped since the planet assembled and cooled only gradually. Part of it can come from slow gravitational settling, as heavier components sink and release potential energy as heat. Even the act of separating materials, layer by layer, can keep the interior warm over billions of years. We cannot drill into Neptune, so the structure is inferred rather than observed, and inference has to be disciplined. Gravity measurements constrain how mass is distributed, because a spinning planet tugs on a spacecraft in measurable ways. But gravity does not give a single answer, and different interiors can cast similar gravitational shadows. The main direct encounter we have is brief, and it still shapes nearly every model. Voyager 2 flew past Neptune in 1989, measuring the gravity field, the radio signal through the atmosphere, and the magnetic environment. That single pass was a revelation, but it was also a reminder of how much remains hidden. Interior models fit the same data with different layer boundaries and compositions, because the planet is not obliged to be neatly separated. Scientists adjust equations of state, relationships between pressure, temperature, and density, to see which interiors match the measured gravity harmonics. The results are a family of plausible Neptunes, not one final cutaway. Still, a broad picture emerges, and it is the best map we have, even if the borders are drawn in pencil. An outer hydrogen and helium envelope surrounds a mantle rich in the planetary ices, meaning water, ammonia, and methane in some mixture. Deeper still, a denser core likely concentrates rock and metal, though its size and state remain uncertain. When we say envelope, we do not mean a thin skin, because this region can extend thousands of kilometers. Hydrogen and helium dominate by volume, and they control the planet's radius, its weather, and much of its visible personality. Yet they may represent only a smaller fraction of the total mass than the deeper, heavier materials. The boundary between envelope and mantle is not a hard shell, and it is not a clean chemical wall. It is a transition where pressure forces molecules closer, and mixtures become more complex as solubility and reactivity change. In that region, gas and liquid stop being cleanly separate behaviours, and the planet slides into a new regime. A useful way to picture it is as a gradual thickening, where the atmosphere becomes so dense it behaves like a liquid without a shoreline. The clouds we see from space are only the uppermost weather layer floating above a deepening fluid. The familiar idea of down still applies, but the medium becomes increasingly continuous and heavy. The mantle is where the word ice becomes actively misleading, because the compounds we label as ices are no longer cold. Under Neptune conditions, water, ammonia and methane are not expected to sit as familiar solids. They are compressed into hot, dense fluids that can behave like oceans without shores, stirred by convection and shaped by pressure. In this deep fluid world, the distinction between ocean and atmosphere blurs, because both are just phases of matter under different conditions. A droplet would not fall the way it does on Earth, and bubbles would not behave like bubbles. The physics is still the physics of molecules, but the rules are rewritten by the squeeze. This is where phase diagrams become the navigation tool, because they tell us what matter wants to be. A phase diagram is a map of state, showing which form matter prefers at a given pressure and temperature. On Earth, we use it to explain boiling and freezing, but Neptune pushes it into alien territory. On a phase diagram, lines mark boundaries between solid, liquid, and gas, and special points mark where those boundaries end. Earth's everyday experience lives near one small corner of that map, where water can be ice, liquid, or vapor. Neptune's interior marches across the diagram into regions we rarely test, where new phases appear and old words lose precision. At millions of atmospheres, the diagram's lines bend and new regions appear, because intermolecular forces and bonding arrangements change. Melting points shift, boiling points lose meaning, and critical points are crossed, where liquid and gas become indistinguishable. The mantle becomes a place where the usual phase words are only approximations and the material is defined by density and conductivity. In the upper mantle, the ices may exist as high-pressure liquids or supercritical fluids, depending on the local temperature gradient. Supercritical means the substance is neither gas nor liquid in the usual sense, because the boundary has been erased. It is a single dense phase that can flow like a liquid and diffuse like a gas, carrying heat efficiently. Supercritical water is not steam and not seawater, but something in between, and it can be startlingly aggressive. Its density can be high, its solvent power extreme, and its chemistry altered by pressure-driven ionization. Under those conditions, materials that do not mix on Earth can dissolve and reactions can proceed along unfamiliar pathways. Ammonia and methane join this mixture, and the combination matters because mixtures do not behave like pure substances. These molecules change the density and the heat capacity of the mantle, affecting how much energy it can store and transport. They also change which phases appear and where boundaries might form, so composition becomes a structural variable. Even small changes in the ratio of water to ammonia to methane can shift the internal profile, because each component responds differently to pressure. Water is polar, ammonia can form hydrogen bonds, and methane is more reluctant to mix under Earth conditions. Under Neptune's conditions, those preferences can change, and the mantle becomes a chemically active blend. The mantle is not guaranteed to be uniform, and that uncertainty matters for the story, because heat transport depends on structure. If composition varies with depth, stable layering can form and slow convection, like a stratified ocean that resists overturning. If mixing is efficient, convection can carry heat upward more freely, feeding the planet's excess radiation. This is the same transport problem that framed Neptune's impossible heat, and it is the reason interior physics matters to weather. Heat must rise through dense material, and the path depends on whether layers overturn or resist, whether buoyant parcels can climb. The mantle is therefore both a reservoir and a gatekeeper, storing energy and controlling its release. Convection itself is a visual process even if we cannot see it directly. In our minds, we can picture slow, towering plumes of warmer fluid rising, while cooler, denser material sinks to replace it. The timescales are enormous, but the motion is real, and it shapes the planet's long-term behavior. As pressure increases further, Water can enter ionic and superionic regimes, and the change is not subtle. In an ionic fluid, molecules partially dissociate into charged components, meaning hydrogen and oxygen no longer stay paired as neat H2O units. Electrical conductivity rises because charges can move, and moving charges are the raw ingredient of a dynamo. This is the first hint of an electrified ocean-like layer, not a metaphor but a physical possibility. Conductive fluid does not need to be metallic to carry current, and it does not need free electrons like a wire. It only needs mobile charges, and high pressure can provide them by breaking molecular bonds and stabilizing ions. In a superionic phase, the picture becomes stranger, and it is one of the most alien states likely inside an ice giant. Oxygen atoms can form a lattice-like framework while hydrogen ions move through it, like a liquid flowing through a solid scaffold. The material behaves partly like a solid and partly like a liquid, and it can conduct electricity efficiently. Superonic water is not just a curiosity, because it changes the mechanical and electrical behavior of the mantle. A lattice can affect viscosity, and viscosity affects how easily convection can move material. If the mantle becomes more resistant to flow in some regions, the dynamo and the heat engine may be forced into particular geometries. Whether Neptune's mantle contains superonic water, everywhere is not settled, because the interior profile is model-dependent. The exact pressure and temperature profile depends on assumptions about composition, mixing, and how much heat is trapped below. But the possibility is central because it changes what the mantle can do both thermally and electrically. Laboratory experiments help, but they are hard because recreating Neptune's interior means compressing materials to extreme pressures while heating them intensely. Researchers use diamond anvil cells and shock compression to probe these regimes, then compare results with quantum simulations. Each experiment draws a small patch on the phase map, and the planet fills in the rest. If the mantle conducts, it can couple to motion and generate magnetic fields, turning heat into organized force. A dynamo needs moving conductive fluid and enough energy to keep it moving, and it needs that motion to persist over long times. Neptune's internal heat provides the motion, and the mantle may provide the conductivity, so the ingredients can coexist. This connects directly to the depth question from the wind chapters, because electricity and motion do not ignore each other. If winds extend deep, they may interact with conductive layers and feel magnetic drag, which can slow or reshape flows. If winds are shallow, the dynamo region may be decoupled from the visible jets, hidden beneath a quieter interface. The interior also rewrites chemistry, not just physics, because pressure can destabilize familiar molecules. Under extreme pressure, carbon-bearing molecules can become unstable in their familiar forms, and bonds can rearrange. Methane can break apart, and carbon can reorganize into heavier structures, depending on temperature and local composition. If carbon separates from hydrogen, it can condense into solid phases at depth, where pressure favors dense structures. Over time, that process could produce diamond formation and sinking, a rain that falls through hot fluid, glittering only in theory. The image is vivid, but the mechanism is what matters, because it implies differentiation inside the mantle. If diamonds or other carbon-rich solids form, they would be denser than the surrounding fluid and tend to sink. That sinking would release gravitational energy as heat, adding another way the interior can stay warm. We do not treat diamond rain as a settled fact, because the pathway depends on composition and temperature, and Neptune is not a laboratory sample. Laboratory experiments and simulations show plausible routes under giant planet pressures, especially for methane-rich mixtures. Neptune's mantle provides the stage where such routes could operate, but the script is still being tested. The mantle's behavior also affects how storms and vortices might be fed from below, even if the connection is indirect. Deep convection can rise from water-rich layers, carrying heat and material upward toward the weather layer. That convection could seed waves and instabilities that shape the jets above, giving storms an internal heartbeat. Imagine a rising plume reaching a boundary where density changes quickly, spreading sideways like smoke under a ceiling. That spreading can generate shear, and shear can roll into vortices, which can then migrate and merge. The visible storm is the surface signature of a deep process, translated through layers we cannot see. The link is indirect but important for the central question, because energy must travel before it can be spent. Winds and storms are the visible spending of energy, while the mantle is the bank that holds the principle. If the bank is layered, the spending may be episodic, and storms may appear and vanish quickly, as if the planet were breathing. Uncertainty is not a weakness here. It is a constraint we must respect, because Neptune does not offer easy measurements. We infer interior structure from gravity harmonics, rotation, and bulk composition, and each measurement has limits. Without an orbiter, multiple interior models remain consistent with the same limited data, and we have to live with that ambiguity. Rotation itself complicates the inference, because a spinning planet is flattened and its mass distribution affects the gravity field. Differential rotation, if it extends deep, can also alter the measured harmonics, blending weather with interior. The result is a puzzle where dynamics and structure are intertwined, and separating them requires careful assumptions. Even the core is an inference drawn from density and formation theory, and it may not resemble a simple ball. It may be a distinct rocky core, or it may be a diffuse region where heavy elements are mixed into the surrounding mantle. Its temperature could be thousands of Kelvin, and its pressure tens of millions of atmospheres beyond any direct sampling. At those pressures, materials we call rock can soften and flow over geologic time, because rigidity is a matter of conditions. The core is not necessarily a rigid ball like Earth's mantle rock feels to us, where solidity is familiar. It may be a hot, dense region that participates in slow circulation, exchanging material with the mantle above. The deeper we go, the more Neptune becomes a planet of gradients rather than layers, and that is a profound shift in perspective. Pressure, temperature, and composition change continuously, and boundaries blur into transition zones that may be hundreds or thousands of kilometers thick. The neat textbook cutaway is a useful fiction that hides complexity, but it still guides our thinking. Still, the layered model is a powerful organizing tool, because it ties observable features to hidden structure. Hydrogen and helium dominate the outer envelope and set the planet's radius and visible weather, including the clouds we track. The ice-rich mantle holds much of the mass and much of the heat capacity, so it governs the long-term thermal budget. The mantle is also where conductivity likely becomes significant, and that conductivity is more than a detail. That conductivity is the bridge between thermal energy and magnetism, linking heat flow to field generation. It is the reason an ice giant can have a magnetic personality, even without an Earth-like iron ocean. Phase diagrams tell us why this is possible, and they make the strangeness rigorous rather than poetic. Under Neptune conditions, water does not have to be ice, and ice does not have to be solid, because phase depends on pressure and temperature. The same compounds can be fluid, ionic, or superionic depending on depth, and each state changes what the planet can do. This is the otherworldliness that matters, because it is physical rather than decorative, and it has consequences. Matter changes its rules when squeezed and heated beyond Earth experience, and those rule changes affect heat transport and electrical behavior. Neptune's interior is an alien laboratory built from common molecules, and that combination is what makes it unsettling. We return to the hook with new meaning because the blue is no longer the story, only the cover. A blue world can whisper at the top and still burn below, with heat rising through layers that look serene from space. The terror is not that Neptune is cold, but that cold is only the skin, and the skin is thin. If there is an electrified ocean-like layer in motion, it can generate a magnetic field, and that field can reach far into space. And Neptune's field is not simple, not centered, and not politely aligned, as if the dynamo were built off axis. That is the next descent, from matter into force, and it begins where conductivity meets motion. The same interior that may forge diamonds can also bend space around the planet with magnetism, shaping charged particles and auroras. To explain Neptune's strange magnetic field, we follow conductivity into the moving dark and we ask what kind of engine could make a field so strange. Neptune's blue face hides a force we can measure, even when we cannot see it directly. Magnetism leaks outward into space, carrying a map of motion inside the planet, an invisible sketch drawn by moving charge. On screen, Neptune hangs like a polished sapphire with thin clouds sliding over a darker, deeper blue. The sunlight out here is weak and angled, yet the planet still announces itself through physics that does not need light. Voyager 2 arrived in 1989 with instruments tuned for fields and particles, built to listen to the quietest whispers. It had already visited Jupiter, Saturn and Uranus, so its team knew what a normal planetary field looked like. As the spacecraft raced in, its magnetometer boom, extended away from the spacecraft's own electrical noise, began sampling Neptune's environment. In minutes of closest approach, it traced a magnetic signature that refused to behave like a simple bar magnet. Earth's field is roughly a tidy dipole, aligned near its spin axis, and it looks clean at large distances. If you draw it, the lines arc from one hemisphere to the other in a familiar pattern, like iron filings around a magnet. Neptune's field is strong, but it is crooked and displaced, and the mismatch shows up immediately in the data. The readings did not just change in strength, the direction swung in a way that implied a rotating off-center source. Voyager measured a magnetic axis tilted far from Neptune's rotation axis, a misalignment that forces the field to sweep through space. It also found the field's effective source offset from the planet's center, as if the magnet were mounted inside a moving shell. That offset matters because a centered dipole is what you expect from a deep, symmetric generator. Neptune instead looks like a magnet built off-axis, inside a planet that should, at first glance, be layered and orderly. The result is unsettling because it is precise, not speculative, and it comes from a clean physical measurement. The spacecraft watched the field direction swing as it flew by, then fit the data with multipoles that describe how complicated a field must be. In that mathematical language, a dipole is only the first term, the simplest shape you can make. Quadrupoles and octopoles add lobes and twists, and they become important when the source is shallow or irregular. Higher order components were unusually important at Neptune, implying complexity close to the source rather than smoothed out by distance. A distant dipole would blur those wrinkles before they reached space, the way a faraway light looks like a point. If you could visualize the solution, you would see field lines emerging from unexpected latitudes, bending sharply and re-entering far from where symmetry would place them. The planet's magnetism looks less like a compass needle and more like a shifting three-dimensional sculpture. This is the first tension point in the chapter. A planet in near darkness still builds an organized field, yet the geometry looks unstable. Magnetic fields are not decorations around planets, and they are not optional features you can add later. They are consequences of moving charge, and moving charge demands a conductive interior that can sustain electric currents. A dynamo is the simplest explanation, and it is a strict one with requirements you cannot negotiate. You need an electrically conducting fluid, sustained motion to move charge around, and rotation to organize that motion into something coherent. Start with the basic idea of induction, a principle discovered in the 19th century and now used in every power grid. When a conductor moves through an existing magnetic field, it generates electric currents, because charges feel a force that pushes them sideways. Those currents create their own magnetic field, and that new field can reinforce the original one if the geometry is favorable. If the feedback is strong enough, the system becomes self-sustaining, meaning the field helps create the currents that maintain the field. This is why dynamos are often compared to generators, even though there are no coils you can point to. They turn mechanical motion into electromagnetic structure, and the wiring is the fluid itself, endlessly rearranged by heat and rotation. But a dynamo is also a balancing act, because magnetic fields fight back against motion. A strong field can resist the very flow that created it, so the system settles into a dynamic equilibrium rather than running away. Rotation is the stabilizing ingredient, and it does more than merely spin the planet. In a rotating body, the Coriolis effect organizes convection into columns and spirals that persist, guiding rising and sinking fluid into patterns that can maintain large-scale currents. Convection supplies the motion because heat makes fluid buoyant, and buoyancy is relentless. Warm, less dense material rises, and cooler material sinks to replace it, creating a continuous overturning that can last for billions of years. If the fluid conducts, that churning acts like a constantly stirred circuit, with charge carriers dragged along for the ride. The planet becomes a machine that writes its interior flow into space, and the writing is legible to a passing spacecraft. Earth's dynamo lives in liquid iron, deep in the outer core where temperatures are high enough to keep metal molten. Iron is an excellent conductor, and Earth's field is therefore dominated by a centered dipole, with higher order terms present but usually weaker. Earth also benefits from a geometry that is comparatively simple, because the conducting region is a thick, roughly spherical shell around a solid inner core. That symmetry does not guarantee stability, but it favours a dipole that looks orderly at large distances. Neptune cannot use the same design because its bulk composition is different and its interior is not metal-dominated. Its deep interior is not an iron ocean wrapped by rock, and the ingredients that conduct electricity must come from another phase of matter. Neptune is an ice giant, meaning water, ammonia and methane dominate much of its mass, mixed with hydrogen and helium above. Under pressure, those ices stop behaving like familiar molecules, and the word ice becomes shorthand for chemistry rather than temperature. At intermediate depths, water and ammonia mixtures can become ionic, which means molecules partially dissociate into charged fragments. Mobile ions carry current through the fluid, so the material begins to act less like a neutral liquid and more like an electrolyte under extreme conditions. Conductivity rises sharply when pressure and temperature push electrons and ions into freer motion, and the transition can be dramatic. A salty ocean is conductive on Earth, and an ionic ocean is conductive on Neptune, even though the chemistry is far stranger. In laboratory experiments and computer simulations, water at high pressure does not simply compress like a sponge. Bonds bend, electrons shift, and the fluid's ability to transport charge changes, sometimes by orders of magnitude across relatively small depth ranges. This is the chapter's central inference, and it is grounded in that physics of phase change. Neptune's strange field suggests the dynamo operates in a shell closer to the surface, where an ionic mixture can flow vigorously while still conducting well. A shallow dynamo naturally produces a tilted offset field because the generator is not centered in the planet's mass. If the conducting region is not centered, or if it is thin and asymmetric, the dipole can shift away from the geometric center. A shallow dynamo also preserves higher order structure because multipoles decay quickly with distance from their source. Seeing them strongly implies a source not too deep, since a deeper origin would let the complex terms fade before reaching space. The idea is not that Neptune lacks a core, and the planet almost certainly has one of heavier material. The idea is that the main generator may sit above it, in a mantle layer that can flow and conduct, turning a middle zone into the dominant engine. This is where the earlier descent through the mantle pays off, because composition and phase are doing the heavy lifting. The same region that may host exotic water phases can also host electrical currents, and those currents are what Voyager indirectly detected. Models place the likely dynamo in a zone of hot, dense water-ammonia-methane fluid, enriched by dissolved components under pressure. It may be thousands of kilometers below the clouds, yet still shallow by planetary standards because Neptune is so large. In a visual cutaway, the cloud tops become a thin skin, and below them the mantle swells into a vast dark ocean of compressed chemistry. The narrator's words ride over a slow descent, with pressure and temperature readouts climbing as if on an elevator into another world. Some scenarios include superionic water deeper down, where oxygen forms a lattice and hydrogen moves through it, like a fluid within a solid. That phase can conduct, but it may be too viscous to churn efficiently, and viscosity can suffocate a dynamo. So the dynamo may prefer the layer above, where the fluid is ionic and mobile, and where convection can keep renewing currents. The generator needs motion as much as it needs charge, and those two requirements do not always overlap at the same depth. This is why Neptune's magnetism is a clue to hidden layering, not merely a curiosity about compass directions. The field geometry hints at where viscosity changes, where composition changes, and where convection can operate without being throttled. It also loops back to the central question about winds, because the atmosphere is not entirely isolated from what lies below. If the dynamo region is shallow enough, atmospheric jets may couple to it through conductivity and drag, especially where ionized species exist. Conducting fluid moving through a magnetic field experiences magnetic braking, a kind of electromagnetic friction that converts kinetic energy into heat. Fast flows can be resisted, not by air pressure alone, but by the field's tendency to oppose changes in motion. That braking could limit how deep the fastest winds can extend, even if the upper atmosphere wants to shear and race. It offers one physical boundary between the screaming weather layer and the deeper engine, a boundary written in electromagnetic terms. Yet the coupling is subtle, and it depends on how conductivity changes with depth and composition. A small increase in ion content can change how strongly a flow feels the field, so the planet's chemistry becomes part of its meteorology. But without an orbiter, we cannot map that boundary cleanly, and we cannot watch it evolve over time. we have a flyby snapshot, not a long-term survey of field changes, rotation signatures, and the slow drift that reveals interior dynamics. Voyager's measurements also revealed a magnetosphere with unusual geometry, and that geometry is a direct consequence of the crooked field. Because the field is tilted and offset, the magnetosphere is lopsided and time variable, like a shield that never holds still. As Neptune rotates, the magnetic poles sweep through space like a misaligned beacon, tracing circles that do not match the planet's geographic poles. The solar wind meets a moving target and the boundaries shift, compressing and relaxing as the field orientation changes. In a wide shot, the solar wind is drawn as a pale stream, and Neptune's magnetosphere bulges on one side while pinching on the other. With each rotation, the whole structure wobbles, and the boshock and magnetopores breathe in response. Charged particles follow magnetic field lines, so their paths become complex rather than neatly trapped in symmetric belts. Regions of trapping, precipitation, and loss can change with rotation phase, because the field lines themselves are sweeping through different spatial regions. This matters for auroras, which are not just polar lights and not just a pretty afterthought. Auroras are energy transfer, linking space plasma to the upper atmosphere through magnetic funnels that accelerate particles downward. On Earth, auroras cluster around magnetic poles that are relatively stable, so the ovals are persistent features. On Neptune, the poles wander in latitude and longitude as the planet spins, and that wandering reshapes where the funnels connect. That wandering can spread auroral zones and make them intermittent, appearing in places that would look wrong on a more orderly planet. It can also change where particle energy is deposited, altering local heating and driving chemical reactions high in the atmosphere. Upper atmosphere heating is not a small detail on a cold world where sunlight is scarce and weak. In thin sunlight, any extra energy source can reshape chemistry and winds at high altitude, changing how gases mix and how temperatures vary with latitude. So magnetism becomes another coupling mechanism between inside and outside, and it operates continuously. The interior drives the dynamo shapes the magnetosphere, and the magnetosphere feeds energy back into the atmosphere through particles and currents. This is where the stakes rise for the documentary's broader mystery, because Neptune's weather is not only a heat problem, it is also an electrical environment problem, where fields and plasmas can influence how energy is distributed above the clouds. A crooked field complicates how momentum and energy move through layers, and it challenges the idea of clean separation. It may influence how waves propagate, how ions drift, and how the upper atmosphere responds when the solar wind changes. It also reframes the contrast with Uranus, Neptune's near twin, because the similarity is too striking to ignore. Uranus also has a tilted, offset field, suggesting both ice giants share shallow dynamos and that their interiors share a crucial conductive layer. Yet their heat budgets differ sharply, with Neptune radiating far more internal energy than Uranus does. That difference hints that similar dynamo layers can be fed by different convective vigour or inhibited by different internal stratification. Neptune's dynamo therefore becomes a diagnostic tool, not just a measurement of magnetism for its own sake. If convection is stronger or less inhibited than on Uranus, the field may be more active and variable even if the geometry is similarly skewed. We cannot confirm variability with one pass, and we cannot watch the slow changes that would reveal the dynamo's heartbeat. We can only say the geometry is strange enough to demand a non-Earth-like interior, and that the simplest explanation points to a shallow, conducting shell. The chapter's tension comes from how we know what we cannot see, using instruments that translate invisible forces into numbers. We cannot watch the ionic ocean churn, but the field lines betray its motion, and the betrayals are consistent with known electrodynamics. Magnetometers measure direction and strength, then physics translates those numbers into constraints on conductivity and flow, even with limited coverage. The planet's secrecy is real, but it is not total, because a magnetic field is a public signature. Still, the inference has limits, and we should keep them explicit because science is strongest when it names uncertainty. Different interior models can reproduce similar external fields, especially with sparse sampling, and a single trajectory cannot capture every harmonic. The flyby geometry matters too because Voyager sampled only certain latitudes and local times. If you want a full map, you need repeated passes that crisscross the planet, building a global solution rather than a best fit from a narrow slice. A dedicated orbiter would change the game, and it would do so in ways that are almost mundane but profoundly powerful. Repeated passes would map the field in detail, track secular variation, and reveal how deep rotation is shared between layers. Gravity mapping would complement magnetism, separating deep winds from shallow jets by their mass signatures and their subtle tug on a spacecraft. Together, they would test whether magnetic drag sets the wind depth and whether the Dynamo region truly sits close enough to matter. Until then, Neptune's magnetism remains a crooked fingerprint, pressed into space by a hidden hand. It says the Dynamo is not a central furnace like Earth's, but a shell of electrified fluid, offset and tilted in a way that forces complexity outward. That shell is not a calm ocean, and it is not a gentle sea under a quiet sky. It is a conductive, convecting layer under crushing pressure, where chemistry is forced into charged forms, and where heat drives motion that never pauses. The same pressure that makes fluids conductive also makes molecules unstable, and instability is a kind of creativity in planetary interiors. Methane can break apart, and carbon can reorganize into denser structures because high pressure rewards compact arrangements. In a visual sequence, methane molecules are shown as familiar tetrahedra, then squeezed until bonds distort and snap. The animation slows as atoms rearrange, and the scene darkens, suggesting depth, heat, and the weight of kilometers of fluid overhead. This is the next descent in the story, and it follows naturally from the last because conductivity and chemistry share the same cause. As pressure rises and chemistry transforms, carbon may crystallize and fall through the mantle, changing the interior's composition as it goes. We leave the crooked magnet with a final implication, and it is both scientific and philosophical. Neptune's field is a warning that the interior is active, layered, and electrically alive, and it invites a question about how many hidden oceans exist in the universe. What does it mean that a planet can hide its engine so completely, yet still broadcast its shape through magnetism alone? Out here, far from the sun, Neptune proves that darkness does not equal stillness, and that motion can be inferred from the faintest signals. Neptune looks calm from far away, but the calm is only a lid, an optical illusion painted by high clouds and distance. Beneath that pale blue skin, pressure and heat turn chemistry into a machine, and the machine never truly rests. The central question tightens again in this chapter, because Neptune refuses to behave like a dead, frozen orb. How can a cold, dim planet drive violent winds and still run deep reactions that may forge diamonds? That puzzle is not poetic. It is an accounting problem for energy, materials, and time. We have already followed heat into the mantle and charge into the crooked dynamo, where motion becomes magnetism. Now we follow carbon, because carbon is where Neptune's beauty becomes unsettling. Carbon is familiar on Earth, yet inside an ice giant it becomes a phase diagram story written at impossible pressures. Methane is a trace gas in the upper atmosphere, and it helps tint Neptune's visible colour by absorbing red light. Yet methane is also a major carbon carrier in the deep inventory, mixed into a mantle that is neither simple ice nor simple gas. In Neptune's interior, methane is not a stable, gentle molecule, and its familiar shape becomes negotiable. At Earth conditions, methane is simple and stubborn, with carbon locked to 4 hydrogens in a tidy tetrahedron. Those CH bonds are strong enough that methane can persist for ages in cold environments, and it often behaves like a chemically quiet fuel. Under Neptune conditions, the same bonds can become liabilities because the environment supplies both crushing confinement and relentless thermal agitation. Pressure rises by the weight of everything above, and it rises without mercy for thousands of kilometers of overlying fluid. Temperature rises too because internal heat is trapped and transported imperfectly, and because compression itself stores energy as warmth. Even without sunlight, the deep interior carries a thermal memory of formation and evolution. In that regime, hydrocarbons can dissociate, meaning CH bonds break and atoms reorganize into new arrangements. The driver is thermodynamics, not imagination, and the rules are written in free energy rather than in human expectations. When conditions change, the most stable arrangement changes with them, sometimes abruptly. High pressure favors dense phases, because dense structures minimize volume and lower free energy under compression. High temperature accelerates reactions, because it helps bonds break and reform, and it allows atoms to explore more configurations per second. Together, pressure and temperature act like a vice and a furnace, squeezing and stirring the same material until it finds a new equilibrium. The hypothesis begins with a simple step, and it is simple only in outline. Methane is squeezed and heated until it decomposes into hydrogen-rich fluid plus carbon-rich fragments, with intermediate molecules flickering in and out of existence. Instead of one clean split, the system can pass through short-lived chains, rings, and polymer-like structures. The chemistry is not one clean equation, and the pathway depends on mixture and local conditions inside the mantle. Neptune's interior is expected to contain water, ammonia, methane, and hydrogen, and each ingredient changes what reactions are favoured, but the core idea is consistent with known high-pressure behaviour of hydrocarbons, where carbon tends to seek denser bonding networks. When carbon separates, it does not have to remain as soot-like clusters drifting in a fluid. Under sufficient pressure, carbon's stable form can shift toward diamond rather than graphite, because diamond packs atoms more tightly. Graphite is comfortable at low pressure, but diamond is the compact answer when the universe demands less volume. This is a carbon phase transition story, and it is why the word diamond belongs in planetary physics. Diamond is not rare in principle. It is rare because Earth's surface conditions do not favour it, and because the path from deep formation to surface survival is narrow. On Neptune, the path to formation may be broad, even if the path to preservation is uncertain. On Earth, diamond is metastable at the surface and stable only at high pressures deep in the mantle. That is why natural diamonds are associated with deep origin rocks, and why they arrive through violent transport rather than gentle weather. Neptune offers pressure on a planetary scale sustained for billions of years, and it supplies a vast laboratory where carbon can be forced into its densest common lattice. The next step is nucleation, the birth of a solid from a fluid, and it is the quiet gatekeeper of the whole process. A few carbon atoms assemble into a seed that is stable enough to keep growing, and that stability depends on surface energy as much as bulk thermodynamics. In plain terms, tiny crystals are fragile because their surfaces cost energy. Nucleation is hard because small clusters tend to dissolve back into the fluid, erased by thermal motion before they can become real. It becomes easier when the fluid is supersaturated in carbon, and when pressure stabilizes the dense lattice, tipping the balance toward persistence. The mantle does not need perfect conditions everywhere. It needs pockets where the balance favors growth. Once a nucleus forms, growth can proceed by adding more carbon from the surrounding mixture, atom by atom or in small bonded fragments. The grain becomes a crystal, and the crystal becomes a particle with weight, and weight matters in a gravity field. Even in a convecting mantle, density differences create a slow, persistent bias. This is where the famous phrase diamond rain tries to compress an entire physical process into 2 words. The rain is not near the clouds, and it is not a glittering shower in sunlight, and it is not a spectacle for any eye. It is a hidden precipitation inside a planet, occurring where light never reaches and where matter behaves like a compressed reactive sea. It would occur far below the visible atmosphere in darkness, at pressures of millions of atmospheres and temperatures of thousands of Kelvin. The setting is a hot, dense, fluid mantle, where hydrogen-rich components can behave like a supercritical solvent, and where ice is a misleading word. The visuals are not droplets and air, but rolling layers of opaque fluid threaded with gradients. If you could descend through that interior in imagination, the sky would vanish quickly into a dim haze of deepening blue. Then the blue would be swallowed by black, and the sense of space would dissolve into pressure and heat. What replaces weather is circulation, slow, massive overturning that moves heat, composition, and charge. We should separate what is supported from what is still speculative, because Neptune invites overconfident stories. The interior composition is inferred from mass, radius, and gravity harmonics, and the exact pressure-temperature profile is model-dependent. Even the boundary between mantle and core may be a gradient rather than a clean interface. Yet the underlying physics is testable in pieces, and researchers have tested pieces with remarkable ingenuity. High-pressure experiments show that hydrocarbons can break apart, and that carbon can condense into diamond under extreme compression, even when the starting material is chemically simple. The experiments cannot recreate a planet, but they can interrogate the same phase behavior. In diamond anvil cells, scientists squeeze carbon-bearing samples to enormous pressures between 2 gem-quality diamonds, then heat them to drive reactions. The sample is tiny, sometimes smaller than a grain of sand, and it is watched through microscopes and measured with spectroscopy. But the phase behavior is real, and it follows reproducible boundaries that can be mapped. In shock and laser-driven compression, pressure and temperature spike rapidly, mimicking some aspects of giant planet interiors in a violent instant. These experiments can push into regimes that static presses struggle to reach, and they can probe how quickly chemistry responds when matter is forced far from its usual state. The timescales are short, yet the transformations can be decisive. Results from several approaches suggest diamond formation from hydrocarbon mixtures, including methane-rich compositions, under conditions comparable to ice giant mantles. In some experiments, diagnostic signatures indicate crystalline carbon, and the inferred structures match diamond rather than graphite. The evidence is not a direct observation of Neptune, but it is a credible analogue built from controlled extremes. There is historical context here because the idea did not appear from nowhere. For decades, planetary scientists have used phase diagrams to predict what materials do at depth, and carbon's phase diagram is one of the most studied. As laboratory techniques improved, the old theoretical suggestion that carbon could precipitate as diamond inside ice giants became something you could test rather than merely debate. The limits matter because a planet is not a laboratory pulse, and it does not reset between trials. Experiments are short, samples are simple, and Neptune's mantle is a mixed, convecting, electrically active environment with gradients and impurities. In a planet, reactions can be aided or hindered by transport, by stratification, and by the slow churn of convection. Scaling from millimeters to thousands of kilometers requires models, and models carry assumptions about mixing, gradients, and reaction times. The hypothesis survives because it fits the physics, not because it has been photographed, and that distinction is crucial. Neptune is distant enough that even its basic interior layering is still an inference. If diamond formation occurs, the next question is mechanical rather than chemical, and it is where the word rain earns its metaphor. How does a solid behave inside a deep, dense, fluid world, where viscosity and turbulence can be very different from anything in Earth's oceans? A solid particle is not just a crystal, it is a moving object with drag, buoyancy, and collisions. A diamond grain is denser than the surrounding hydrogen-rich fluid, so gravity gives it a direction, even in a churning mantle. It should settle downward, even if the surrounding mantle is convecting, because the density contrast creates a net downward force. The details depend on grain size, fluid viscosity, and the vigour of convection around it. The settling is not necessarily smooth, because the mantle is moving and stratified in places, and stratification can act like a barrier. Upwelling can slow descent, and turbulence can keep small grains suspended longer, especially if they are tiny and numerous. In a thick fluid, the difference between drifting and falling can be a matter of millimeters per second, sustained for ages. Still, over time, dense solids tend to sink in a gravitational field, and that tendency is one of planetary science's most universal themes. Differentiation is a universal planetary process, and Neptune has had billions of years for it to operate, even at slow rates. Time is an ingredient, and Neptune has had more of it than any laboratory can offer. The rain analogy becomes useful here, if we keep it honest and resist turning it into a cartoon. Like hailstones, particles can form, grow by accretion, and then fall when they become heavy enough to overcome local stirring. But the scale is alien, and the medium is not air but a dense reactive fluid. The fall is not through air, it is through a hot, high-pressure fluid that blurs the line between liquid and gas. The fluid may behave supercritically, meaning it has no clear surface and no simple boiling point, and its solvating power can change with depth. A sinking grain moves through a continuum, not through layers that behave like familiar weather. The fall is also not a short trip, and it is not a single uninterrupted drop. It could span thousands of kilometers, across regions where viscosity, conductivity, and composition change with depth, and where convection cells rise and sink like slow-motion storms. A grain might drift, stall, and then resume, its path shaped by a planet-sized circulation. As grains descend, they may continue to grow if carbon remains available in the surrounding mixture, and growth can be self-reinforcing. Larger particles settle faster, which reduces their time in the formation zone, yet collisions can accelerate growth during descent. Some grains may collide and aggregate, building larger pieces that sink faster, and the interior becomes a place where size distribution matters. Some grains could dissolve again if they enter zones where temperature is too high for diamond stability, or where the chemistry favours carbon returning to the fluid. Neptune's interior is not uniform, and stability depends on local pressure and temperature, not on the romance of gemstones. A diamond is stable only where the phase diagram says it is stable. That creates a layered possibility, and it is more interesting than a one-way rain. Diamond may form in one band of conditions, sink into hotter regions, and then transform or redissolve, feeding carbon back into the fluid. The cycle could be partial and messy, but even a partial cycle can transport material and energy. Even that cycle would matter, because it moves material and releases energy, and planets run on such bookkeeping. A planet does not need permanent gemstones to use the process as an engine, and it does not need a glittering outcome to gain heat. The act of separation and sinking is already a physical transaction. This is where diamond rain connects back to the hidden furnace, and the connection is not metaphorical. When mass moves downward in a gravity field, gravitational potential energy is converted into heat, either by frictional dissipation or by stirring that ultimately becomes thermal energy. The energy per kilogram is not mystical. It is the same accounting that drives differentiation in many worlds. If carbon-rich solids separate and settle, Neptune can gain an additional heat source beyond leftover formation heat and slow contraction. The contribution is uncertain, but the mechanism is plausible, and plausibility matters when you are balancing a planetary energy budget. Neptune emits more energy than it receives from the Sun, and every credible internal source deserves scrutiny. The uncertainty is not only about chemistry, it is about rate, and rate is what turns a mechanism into power. How much carbon is available, how fast it separates, and how efficiently it sinks determine the power, and each factor is difficult to constrain remotely. A slow drizzle over billions of years can rival a brief torrent depending on totals. If the mantle is strongly stratified, separation could be slowed, and heat transport could be throttled, leaving energy trapped below. If the mantle mixes vigorously, reactions and settling could be more continuous, and the released energy could be carried upward more effectively. Which picture is closer to reality is still debated, and Neptune's distance keeps the debate alive. This loops back to the storm problem, because storms are the spending of energy that must be delivered upward through convection and waves. Any process that adds heat at depth can help sustain convection that feeds winds and vortices, even if the connection is indirect and delayed. The atmosphere is the visible bill for an invisible interior budget. It also loops back to Uranus, because Uranus appears thermally quiet compared with Neptune, despite their similar sizes and compositions. If their interiors differ in layering or mixing, the same chemistry could yield different heat outcomes, and the same carbon could behave differently. That contrast is a reminder that small differences in structure can produce dramatic differences in behaviour. Diamond rain is therefore not just a spectacle, even if the phrase invites spectacle. It is a candidate piece of the energy budget that might help explain why Neptune screams while its near twin whispers. The question is not whether diamonds are pretty, but whether differentiation is active enough to matter. We should keep the hierarchy clear because Neptune's heat excess does not require diamonds to exist. Neptune's measured heat excess is real, and diamond rain is a possible contributor within that budget, not the entire explanation. Primordial heat and slow gravitational contraction remain major suspects, and they can dominate even if diamonds form. The diamond hypothesis matters because it is a concrete differentiation pathway tied to composition, and it can be evaluated against experiments and models. It links microphysics, bond breaking and crystal growth, to macrophysics, heat flow, mixing, and long-term evolution. That bridges the real scientific value of the idea. The narrative peak is the idea that common molecules become treasure under pressure, and that treasure is indifferent to human meaning. Methane, one of the simplest hydrocarbons, becomes a feedstock for crystalline carbon in the deep abyss, where the word simple loses its comfort. Under the right conditions, carbon chooses the tightest architecture available. In that abyss, beauty and terror are the same phenomenon at different distances, and Neptune makes that duality literal. A gemstone on Earth is a symbol, but inside Neptune it could be a byproduct of crushing physics, formed without intention, without rarity, and without witness. The planet's interior does not care about value, it cares about stability. Neptune's interior follows phase diagrams, and it rewards dense lattices when pressure makes them stable, even if the result sounds like fantasy. The deeper implication is that Neptune is chemically active, not chemically frozen, and activity means change over time. Its mantle is a reactor where bonds break, ions move, and solids can precipitate out of fluid. That activity can reshape composition over time, changing density profiles that affect gravity harmonics measured from afar. It can also alter conductivity patterns that influence where the dynamo operates, because electrical conduction depends on what phases are present. A mantle that separates components is a mantle that changes its own electromagnetic character, so diamond rain is not isolated from the crooked magnet story, even if they sound like separate mysteries. If carbon separates, it can change the mixture that carries current, and it can shift the dynamo's effective shell, subtly moving where magnetic field lines are born. The magnetosphere we see may be downstream of deep chemistry we cannot see. It is also not isolated from the wind depth question, and that connection is a reminder that Neptune is one system. Conductive layers and magnetic drag may limit deep jets, while internal heat and differentiation drive the convection that feeds the atmosphere. The atmosphere is the surface expression of interior constraints, translated into clouds and speed. But we cannot yet close those loops with direct measurement, and that gap defines modern Neptune science. Without an orbiter, we cannot map gravity and magnetic fields with the resolution needed to test interior layering and ongoing differentiation. We can only build consistent stories from physics, experiments, and the few hard constraints we possess. Neptune forces humility, because it offers a single flyby and a distant glow, and it keeps its decisive data locked inside. Still, the diamond hypothesis is not a fantasy bolt-on, and it is not a decorative myth. It is a disciplined extrapolation from high-pressure chemistry, supported by laboratory analogues and by the logic of dense phases. Now we ask the next question, because the rain has somewhere to go, and the direction is always downward. What happens when diamonds fall past the region where they can form, and what do they meet as the environment grows hotter and stranger? Does the crystal endure, dissolve, or transform into something even denser? They descend toward deeper, hotter layers where water may be ionic or supersonic, and where the boundary between mantle and core becomes a gradient rather than a wall. In those depths, matter can conduct electricity through mobile ions, and the distinction between solid and fluid can become ambiguous. The gemstones approach a realm that can erase them, or store them, or transform them again. The fall, therefore, becomes a bridge to the next chapter's deeper interior, and the bridge is made of pressure. Neptune's treasure does not land on a surface. It disappears into a hotter darkness that still controls the planet's power. The story continues below, where chemistry meets the deepest heat, and the planet's structure becomes most uncertain. The diamonds keep falling, and the abyss below them stops resembling any ocean we know. Neptune's deepest interior is where pressure and temperature rewrite chemistry, then rewrite the meaning of solid and fluid. In the mind's eye, the descent is a narrowing shaft of darkness, cloud tops fading, blues collapsing into black, and the last familiar textures dissolving into gradients. This chapter is the descent's extreme point, where intuition fails first and equations fail next. The central question tightens into a boundary problem. How can a cold, distant planet drive screaming winds while hiding an interior that behaves like an electrified alien sea? The paradox is visual as much as physical. Sunlight weakens with distance, yet the planet's engine refuses to go quiet. Start with the only honest map we have, a pressure and temperature profile built from constraints. Neptune's mass and radius set the average density, and density forces the interior to be compressed and hot. Even before chemistry enters the story, gravity does the first round of work, squeezing matter until it becomes something new. Models place much of the deep mantle at tens to hundreds of gigapascals, with temperatures of several thousand Kelvin. Those pressures rival what Earth's mantle never reaches, and they persist over planetary volumes rather than laboratory millimeters. Those numbers are not decoration because molecular bonds are conditional agreements. At a few gigapascals, familiar ices already stop acting like ice, and liquids stop acting like liquids. The neat categories we learn in school depend on low-pressure rules that Neptune simply does not honor. By tens of gigapascals, hydrogen bonding is distorted beyond recognition, and molecules begin to dissociate into ions. The same atoms remain, but the bookkeeping changes, electrons shift, charges separate, and structure becomes a moving target. Pressure is not just weight, it is a chemical lever that favours compact arrangements. Temperature is not just heat, it is the agitation that breaks and reforms bonds fast enough to reach new equilibria. Together they push water, ammonia, methane, and hydrogen into regimes where phase diagrams become the plot. A phase diagram is a map of stability, and down here the map is crowded with unfamiliar provinces. In Neptune's deep mantle, water is expected to become ionic, meaning H2O does not remain intact. The fluid contains charged species, with protons and hydroxyl-like fragments moving through a dense oxygen-rich background. In plain terms, the water becomes a saltwater-like conductor, but without the salt, its own atoms provide the charges. Conductivity rises because charge carriers are no longer rare, and the liquid becomes an electrolyte at planetary scale. The ocean is not an ocean of waves, but an ocean of charge and motion. Scientists call this an electrified ocean, but the phrase is shorthand, not poetry. It means a thick layer of dense fluid where ions carry current efficiently. It means convection and rotation can turn that current into magnetic field, and that magnetism can push back on motion. Picture a slow boil in near total darkness, warm material rising, cooler material sinking, and every moving charge tracing invisible loops. The deeper we go, the more exotic the same ingredients become. Under higher pressures and thousands of Kelvin, simulations and experiments suggest water can enter a superionic phase. Oxygen atoms lock into a lattice-like structure, while hydrogen ions remain mobile, flowing through the solid framework. The image is uncanny, an ice-like scaffold that holds shape, while the lightest ions race through it like commuters through a rigid city. Superionic water is the chapter's first broken physics moment for human intuition. It behaves partly like a solid, because the oxygen lattice resists shear. It behaves partly like a liquid, because hydrogen moves and carries charge, and that mobility can be high. If you could touch it, it would not feel like ice or water, and it would not behave like either for long. That hybrid matters because Neptune's interior must transport heat outward for billions of years. Convection is efficient when material can flow, and inefficient when viscosity rises or stratification blocks overturning. A superionic layer could conduct electricity well, yet convect sluggishly, changing where the dynamo can actually operate. It can also redirect heat into conduction, which is steady and quiet compared with overturning plumes. So the electrified ocean is not one simple layer, and it may not be stable in time. There may be an ionic fluid zone above, a superionic zone below, and transitions that shift with composition. Small changes in mixture can move phase boundaries by hundreds of kilometers, and that uncertainty propagates upward into every model. Even the ratio of water to ammonia to methane can tilt the balance, because mixtures do not freeze or ionize on schedule. This is where equations of state become the main characters, because we cannot sample the interior directly. An equation of state links pressure, temperature, and density for a given composition. It tells you how compressible a mixture is, how much heat it stores, and how buoyant parcels become as they rise. In narration terms, it is the rulebook that decides whether a blob of fluid floats, sinks, or stalls. But equations of state at these conditions are not fully settled, even for water. Laboratory data are limited, because reaching hundreds of gigapascals and thousands of Kelvin is difficult and often brief. Diamond anvil cells can squeeze steadily, but heating uniformly is hard and samples are tiny. Shock experiments can reach the right pressures, yet they do it in microseconds, long enough to measure, not long enough to relax into equilibrium. Theory helps, but theory depends on approximations about electrons, bonding, and mixtures that are hard to validate. The result is a controlled tension rather than a clean answer. Different equations of state produce different density profiles, and different density profiles change the inferred layering. That changes where convection is vigorous, where it is suppressed, and where the dynamo shell can plausibly sit. A small change in compressibility can shift an entire boundary, the way a small change in tide can redraw a coastline. Neptune's interior is therefore a place where models diverge in the dark. Two teams can match the same mass and radius, yet disagree on how much rock is in the core. They can agree on a magnetic field's existence, yet disagree on which layer actually generates it. The planet becomes a puzzle with multiple correct-looking solutions, each consistent with the few clues we have. Pressure also pushes hydrogen itself toward unfamiliar behavior. In giant planets, hydrogen can become metallic at extreme compression, with electrons moving freely. Neptune is smaller than Jupiter, but deep regions may still approach regimes where hydrogen-rich mixtures become more conductive than expected. Even before full metallic hydrogen appears, the electrons can become less localized, an intermediate state that changes transport properties abruptly. Even without full metallic hydrogen, partial electron delocalization can change conductivity sharply. That matters for magnetic braking, because conductivity sets how strongly flows feel the field. It also matters for heat transport, because conductive and convective pathways compete, and the balance shapes the planet's cooling history. A more conductive layer can short-circuit temperature gradients, while a less conductive one forces heat to ride upward on moving fluid. Now the descent approaches the core boundary, where the word core becomes a question. Neptune likely has a central region enriched in rock and metals, but the boundary may be a gradient, not a wall. Heavy elements can be mixed upward, and volatiles can be mixed downward, creating a compositional staircase. In visuals, the clean cutaway diagram starts to blur. Colours feather into each other, and the boundary becomes a zone. A rocky or metallic core is plausible, but its size is not pinned down. Some models allow a relatively compact core, while others spread heavy material through a broader inner mantle. The difference is not academic, because core size changes the gravity field, the moment of inertia, and the planet's internal heat storage. It also changes how quickly the planet can cool, because heat capacity and thermal conductivity depend on what is actually down there. Compositional gradients can also create stable stratification, which acts like insulation. If heavy material is layered smoothly, buoyant overturning can be suppressed, trapping heat below. That offers one route to long-lived internal energy, and it offers one route to why Neptune stays a furnace. The interior can become a layered cake where some layers refuse to mix even when they are hot. Yet stratification is also a throttle on the dynamo, because dynamos need motion. If a deep layer is too stable, convection weakens and field generation shifts upward. That shift would naturally produce a more complex offset magnetic field, consistent with Voyager's crooked fingerprint. The field we measure far above the clouds becomes a clue to where the interior is still allowed to churn. The depth question returns here with sharper edges. If winds extend deep, they must eventually meet conductive fluid, and then magnetic drag should break them. If winds are shallow, then the coupling is weaker, and the atmosphere becomes a thinner spending layer over a deeper bank. The planet's weather is not just meteorology, it is a probe, pressing on the boundary between air and conductor. The problem is that both pictures can be made to fit limited data. Neptune's visible clouds track winds at the top, but they do not reveal how far momentum penetrates. Without long-term gravity mapping, we cannot separate a shallow jet from a deep one by its mass signature. The atmosphere shows us speed, but it hides the lever arm, so we rely on inference, reading a planet by its pull and its field. Gravity tells us how mass is distributed, because a rotating, layered planet is not perfectly spherical. Magnetic measurements tell us where conductive fluids move, because moving charge writes patterns into space. Between them lies a kind of remote sensing, measuring consequences then reasoning backward to causes. Gravitational harmonics are the first half of that reading. The coefficients, like J2 and higher terms, encode how flattened the planet is and how density varies with radius. They also contain possible contributions from deep winds, because moving mass slightly reshapes the gravity field. In practice, a spacecraft's radio signal becomes a ruler. Tiny Doppler shifts reveal tiny changes in the planet's pull. Voyager provided a snapshot of these harmonics through tracking data, but the snapshot is coarse. The uncertainties allow multiple interior structures, especially when composition is mixed. A dedicated orbiter would tighten these numbers and test whether winds contribute measurably to gravity anomalies. It would also watch the planet long enough to separate transient weather from persistent deep structure. Magnetic measurements are the second half, and they are more dramatic but not more complete. Neptune's tilted offset field implies a dynamo in a shell, not a deep-centered core. The strong higher-order multipoles imply the source is relatively shallow, because complex terms decay rapidly with distance. In other words, if the source were deep and smooth, the field would look simpler by the time it reached space. Yet even that inference has degrees of freedom. A thin shell can be shallow or mid-depth, depending on conductivity and viscosity profiles. a supersonic layer could conduct but resist motion, pushing the active dynamo above it, but that depends on uncertain rheology. Rheology is just the material's willingness to flow, and down here willingness is controlled by phases we barely know. This is where high-pressure physics becomes a detective story with missing evidence. We use diamond anvil cells, shock compression, and laser-driven experiments to probe water, ammonia, and carbon mixtures. We use quantum and molecular simulations to extend beyond measured points, then stitch results into planetary models. The history matters. Voyager's 1989 flyby gave us the magnetic shock, and decades of laboratory work have tried to build the interior that could produce it. The stitching is where broken physics becomes a narrative beat. At Earth conditions, you can separate gas, liquid, and solid with clear boundaries. In Neptune's interior, supercritical regimes erase those boundaries, and the same material can shift character smoothly with depth. The camera would show a gradient instead of an interface. No surface, no waves, just thickening fluid turning into structured matter. Supercritical water is not steam and not liquid, but a dense fluid with changing solvating power. It can dissolve materials that would be insoluble at the surface, including rock components. That means the core may not be isolated, because the mantle could leach and redistribute heavy elements over time. The idea is subtle but profound. Rock can become a solid, and a planet can slowly remix itself. If rock dissolves into supercritical water, the core becomes less like a ball and more like a gradient. That changes density profiles and can sustain stratification that persists for billions of years. It also changes conductivity and opacity, which feed back into heat transport and cooling rate. Opacity is the interior's resistance to radiating heat, and even small changes can alter how the furnace breathes. The interior therefore becomes a coupled system, not stacked layers. Composition affects phase affects conductivity and viscosity, conductivity affects magnetism and drag, and viscosity affects convection and heat flow. Every link in that chain touches the winds we see at the top. When you watch cloud bands race, you may be watching the surface expression of a deep electrical ocean pushing back. This is the chapter's peak tension, because the deepest layers are where our models disagree most. You can match Neptune's bulk density with many mixtures of rock, ice, and gas. You can reproduce a crooked magnetic field with different shell depths if you tune conductivity and flow. The tuning is not cheating, but it exposes how many knobs the planet gives us. So the planet's secrets are not hidden by distance alone, but by degeneracy. Multiple interiors can produce similar exterior signatures, and a single flyby cannot break the tie. Neptune becomes a lesson in inference, where certainty is earned only by narrowing possibilities. What would it take to collapse the options? An orbiter, a seismology experiment, a longer magnetic record, or all of them together? Still, some conclusions are hard to avoid. Neptune must contain a thick region of electrically conductive fluid, because a dynamo requires it. That fluid is likely an ionic water-rich mixture, possibly transitioning to superionic phases deeper down. The dynamo's geometry implies the active region is not a deep symmetric iron ocean. Instead, it is a restless shell, off-center, complicated and alive with moving charge. And Neptune must contain heavy material concentrated toward the center, because its density demands it. Whether that heavy material is a compact core or a smeared gradient remains open. That openness is not a failure, it is the current frontier. The frontier is defined by what we can measure, and by what matter chooses to do under impossible pressure. Now return to Diamond Rain, because it does not end as a metaphor. Carbon that separates and sinks changes composition as it goes, potentially enriching deeper layers. That enrichment can alter density gradients, which can either stabilize layers or trigger new mixing, depending on where the carbon ends up. In a cutaway, you can imagine glittering grains dropping through a dark fluid, then vanishing into hotter depths. If diamonds reach hotter regions where they are no longer stable, they can dissolve or transform. That would recycle carbon into the fluid, changing conductivity and chemistry again. The rain could be a one-way differentiation pathway, or it could be a cycle that transports material and heat. Either way, carbon is not just decoration in the atmosphere, it is an active participant in the interior's bookkeeping. Either way, the deep interior is not static. It is a slow reactor under compression, with phase transitions that can store and release energy. It is a place where the hidden furnace can be fed by contraction, differentiation, and chemical rearrangement, even in near darkness. The timescales are vast, but the physics is immediate. Every atom is pressed into decisions. The conclusion theme returns here with its sharpest edge. Neptune is not a quiet endpoint because its interior is still working, still moving charge, still moving heat, still changing itself. The terror is not monsters in the dark, but matter behaving in ways we barely understand. If you could listen, you might imagine a low, continuous thunder, convection, phase change, and magnetic stress playing out beyond sight. We end this descent by naming what we do not know, because that is where the story's pressure peaks. We do not know the core's exact size, composition, or whether it is sharply bounded. We do not know the exact depth of the dynamo shell, or the viscosity of superionic water. We do not know how deep the fastest winds penetrate, or where magnetic drag finally wins. We do not know whether stratification locks heat away, or whether convection pulses and breaks through in episodes. Neptune's surface weather becomes the visible symptom of an interior we can only read indirectly. After plumbing the abyss where physics turns alien, we pull back to what Neptune leaves behind. Its moons and rings are fingerprints, preserving clues to history, impacts, and the violence that shaped this engine. The camera retreats, out past the cloud tops, out past the faint arcs of ring material, and into a wider stage where debris and satellites keep their own records. We zoom outward, carrying the deepest uncertainty with us. The planet's pull and field gave us a partial map, but its satellites and debris may hold the next constraints. Neptune's secrets are not only inside it, they are also orbiting it. In the cold light near the edge of the solar system, even small moons can become witnesses, silent, circling, and patiently informative. We pull back from Neptune's interior because the planet leaves witnesses in orbit, cold, battered bodies that keep records the atmosphere cannot store. Moons and rings carry scars of capture, tides, and breakups, and those scars persist for eons in the vacuum. From far away, Neptune looks serene, a blue disk with a thin halo. Up close, its neighbourhood reads like a case file. Neptune's system is not a neat family built in place, assembled from a calm disk and left undisturbed. It looks like a frontier outpost shaped by intrusion, collision, and long-term gravitational grinding, where orbits slowly precess and resonances quietly rearrange matter. Even the faintest dust can be a clue, because dust does not last unless something keeps making it. Triton is the central clue, because it does not orbit like a native moon, and it refuses to follow the rules of orderly formation. It moves retrograde, opposite Neptune's rotation, and that reversal is the smoking gun, an orbital signature that points outward, beyond Neptune's birth zone. In a clean prograde disk, most large moons inherit the planet's spin direction as naturally as a whirlpool. A retrograde orbit is hard to build from a calm disk around a young planet, because collisions and gas drag tend to erase the wrong-way motion. It is easier to explain as capture, likely from the Kuiper Belt's population, where icy bodies once swarmed in a thicker, more chaotic ring beyond the giant planets. Triton's density and composition also fit that distant inventory. With abundant volatiles that prefer the cold, capture is not gentle, and it demands a way to lose energy, because gravity alone cannot trap a fast passerby. Triton may have been snagged through a three-body encounter, where one object steals energy and another pays the price by being flung away. Or it could have been slowed by gas drag early on, if Neptune still wore a thin envelope of nebular material. Once captured, Triton's early orbit was probably large and highly eccentric, swinging far out and then plunging close. Tides would have flexed it brutally, converting orbital energy into internal heat, as rock and ice strained and relaxed like a repeatedly bent beam. The physics is simple in principle. Friction turns motion into warmth, but the consequences can be extreme. That tidal heating could have been a system-wide event, not just a moon's private furnace, because Triton's changing gravity would have stirred everything nearby. As its orbit circularized, it would have swept through resonances, pumping eccentricities and other moons and destabilizing their paths. In that period, Neptune's satellite system may have sounded like a slow-motion demolition, with impacts spaced by thousands of years. If Neptune once had a regular set of mid-sized satellites, Triton's arrival could have erased them, either by direct collisions or by forcing their orbits to cross. Some bodies would have been ejected into heliocentric space, while others would have spiraled inward and shattered under tides. Debris from that disruption is one plausible source for today's rings, and it would have seeded Neptune's equatorial plane with fragile rubble. Triton still looks active, which is shocking at this distance from the Sun, where sunlight is a weak, bluish whisper. Voyager 2 saw nitrogen geysers and dark streaks that imply ongoing surface change, as if the Moon is still breathing through cracks. The images show bright plains, darker smudges, and a surface that looks less like an ancient crater field and more like a planet that recently woke. Those plumes suggest volatile-driven geology, with nitrogen ice acting like a seasonal engine that can mobilize material without molten rock. Sunlight is weak, but even weak sunlight can move nitrogen on Triton, because nitrogen changes phase at very low temperatures. A thin atmosphere can form and collapse as seasons shift, and that cycling can transport frost like windblown sand. Voyager's plume models point to a greenhouse-like effect inside translucent nitrogen ice, where sunlight penetrates, warms a layer, and traps gas beneath. Pressure builds until it vents through a weak spot, lofting dark particles that later fall and paint the surface in streaks. In the low gravity, a plume can rise kilometers high, turning a small vent into a visible signature. Yet Triton's deeper activity may not be only seasonal, and the Moon's interior history still matters. Residual tidal heat, radiogenic heat from decaying elements, and phase changes in ices can keep a crust mobile, especially if ammonia or salts lower melting points. Even a modest heat flow can maintain pockets of slush, and slush is enough to reshape terrain over geologic time. Triton's surface is young in places, with few craters compared to ancient worlds, and that is a measurable statement. Crater counts are a clock, because impacts accumulate steadily in the outer solar system, even if slowly. That youth implies resurfacing, and resurfacing implies energy still being spent, either in bursts or in a persistent low-grade churn. The Moon's retrograde orbit also means its long-term future is not stable, because tidal interactions work in the opposite direction from most large moons. Tides should slowly shrink the orbit, draining angular momentum until Triton spirals inward, closer to Neptune's pull. The timescale is long by human standards, but it is short in planetary history. In the far future, Triton could cross Neptune's Roche limit and break apart, when tides overwhelm its self-gravity and structural strength. That would create a massive ring system, briefly turning Neptune into a brighter target, with broad bands that could rival Saturn's from afar. It would also be a reminder that rings can be born late, not only at the beginning. Triton therefore links past violence to future violence, and it does so with a kind of inevitability. It is both a captured relic of the Kuiper Belt and a timer counting down to another breakup, its orbit slowly tightening with every tidal exchange. When we look at Triton, we are watching a story that has not finished writing itself. Neptune's rings are not Saturn's bright, broad bands, and they do not announce themselves easily in reflected light. They are faint, dusty, and incomplete, with clumpy arcs that should not last long, like smoke caught in a moving draft. In enhanced imagery, the rings appear as thin, pale threads, interrupted by brighter knots that seem to defy the smoothing power of orbital motion. The arcs are the puzzle, because orbital motion should smear clumps into uniform rings as particles spread and collide. Something must confine them, or constantly rebuild them, because differential rotation is relentless. A ring particle closer to Neptune orbits faster than one farther out, and that shear should stretch any clump into a continuous ribbon. Shepherd moons provide the leading explanation, and the concept is elegantly gravitational rather than mechanical. Small moons can trap particles in resonances, using gravity to herd dust into narrow regions, where repeated tugs reinforce certain longitudes. The result is a pattern that can persist, even if individual grains are constantly replaced. Galatea is often named as a key shepherd, because its orbit matches resonant patterns near the arcs, and those resonances can act like invisible corrals. In a resonance, a particle's orbital period forms a simple ratio with the moon's, so the gravitational nudges arrive in a repeating rhythm. Rhythm matters in orbital dynamics, because repeated small pushes can outweigh a single large one. But confinement is not perfect, and that imperfection is the point, because it reveals a system still evolving. The rings look like a system in motion, not a fossil preserved since formation, and their structure hints at competing processes. Gravity gathers and organizes, while collisions and radiation forces disperse, and the visible ring is the compromise. Dust is also temporary, because micrometeoroid impacts and radiation forces change particle orbits, and small grains are especially vulnerable. Sunlight exerts a subtle pressure, and charged dust interacts with Neptune's magnetosphere, which can lift and tilt particle paths. Without replenishment, faint rings should fade on short timescales, perhaps thousands to millions of years, depending on grain sizes. Replenishment likely comes from impacts on small moons, or from slow grinding of fragile bodies that orbit near the rings. Each collision makes more dust, and dust makes rings visible because tiny particles scatter light efficiently. The rings, in that sense, are not objects so much as processes, ongoing production balanced against ongoing loss. Ring dynamics therefore imply ongoing change and instability, and they echo the broader theme that Neptune is still active. Even outside the planet's atmosphere, energy is being dissipated, momentum is being traded, and structures are being rebuilt. When we see arcs, we're seeing a snapshot of a moving equilibrium. The rings also echo the interior story, because both are governed by energy flow and dissipation, even if the scales are wildly different. In rings, energy is lost through collisions and spreading, turning ordered motion into heat and random velocities. In the atmosphere, energy is gained from internal heat, and spent as winds and storms, and the bookkeeping is just as strict. In both cases, the system is a machine that never fully stops, because it is always converting one form of energy into another. The rings grind and drift, and the clouds race and fold, yet both are ultimately driven by the same physics: gravity, thermodynamics, and time. The question is not whether Neptune changes, but how quickly, and in what direction. Ice giants may be the most common large planets in the galaxy, and that claim is grounded in statistics rather than poetry. Exoplanet surveys show many worlds between Earth and Jupiter in size and mass, a regime our solar system does not display in the inner regions. The absence here makes Neptune more valuable, because it becomes our closest laboratory for a common outcome. Many of those planets are called mini-Neptunes, because their radii suggest thick, volatile envelopes over dense cores, and their bulk densities imply mixtures of rock, ice, and gas. They may not match Neptune's chemistry, but they rhyme, sharing the same structural idea of a compact interior wrapped in a deep atmosphere. When astronomers measure a transit depth, they are often measuring an atmosphere's scale height as much as a planet's solid body. Understanding Neptune helps interpret those distant spectra and densities, because models need anchors that are physically real. It anchors models of how planets accrete gas, retain volatiles, and cool over time, and it tests how opacity and composition control contraction. When we infer a distant planet's metallicity or cloud deck, we are borrowing assumptions from the ice giants we can study directly. Neptune also tests formation theories at the solar system's edge, where building a large core is difficult because material is sparse and orbital periods are long. Its existence constrains how quickly cores grew and how far material migrated, because a slow process would struggle to finish before the nebular gas vanished. That tension, between time available and mass required, still drives debates about whether Neptune formed near its current orbit or moved outward. If Triton is a captured Kuiper belt object, it also informs the outer reservoir's history, and it makes that history feel less distant. Capture implies encounters, scattering, and a dynamically active early frontier, where objects swapped energy and changed neighbourhoods. It suggests that the Kuiper belt we see today is the remnant of a larger, more stirred-up population. Neptune's crooked magnetic field is another exoplanet bridge, because it hints at a dynamo unlike Earth's iron core. A shallow shell dynamo in ionic fluids may be common in volatile-rich planets, where water, ammonia, and methane become electrically conductive under pressure. The field's tilt and offset are not just curiosities, they are diagnostics of where the conducting layer sits and how it convects. That matters because magnetic fields shape atmospheric escape and radiation environments, and they can influence how an atmosphere survives over billions of years. A planet's habitability context can depend on how it generates magnetism, even if the planet itself is not habitable. When we see a mini-Neptune close to its star, we have to ask whether its field can shield it, or whether the star strips it down to a smaller core. Neptune therefore sits between solar system detail and galactic statistics, and it connects the intimate to the immense. It is close enough to study, yet alien enough to represent a wider class, a bridge between one blue world and thousands of faint, unresolved dots. The more precisely we understand Neptune, the less we have to guess when we interpret the galaxy. We still do not know how deep Neptune's winds go, and that uncertainty is not a minor detail. Cloud tracking measures the top layer, but it cannot reveal the hidden momentum reservoir, or the depth at which jets finally slow. Do the winds penetrate thousands of kilometers, or do they fade beneath a weather layer that is thin compared to the planet's radius? If winds extend deep, they must interact with conductive layers and feel magnetic braking, because moving conductors in a magnetic field generate currents that resist motion. If winds are shallow, the atmosphere is a thin, fast skin, decoupled from the deeper interior and driven by heat leaking upward. Either answer changes how we calculate Neptune's energy budget and internal mixing. We still do not know Neptune's interior layering with confidence, because pressure turns familiar substances into unfamiliar phases. Multiple models fit the same mass and radius, because equations of state remain uncertain, especially for water-rich mixtures at tens of gigapascals. In plain terms, we do not know how compressible Neptune's deep materials are, and that uncertainty propagates into every interior map. We still do not know the balance of Neptune's heat sources, and the balance is the engine's blueprint. Primordial heat, slow contraction, differentiation, and compositional layering can all contribute, and each pathway releases energy differently. A layered interior can trap heat like insulation, while efficient convection can vent it. And Neptune's brightness in infrared suggests the story is not simple. We still do not know where the Dynamo operates precisely, and location matters as much as strength. Voyager's snapshot implies a shallow offset source, but shell depth and thickness remain debated, and different depths produce different field geometries. A dynamo closer to the surface can create a more complex field, because smaller convection cells can dominate the pattern. We still do not know the true role of diamond rain, even though the idea is rooted in real high-pressure chemistry. Experiments support carbon condensation at high pressure, yet the rate and energy contribution are unconstrained, and the process may occur in layers rather than everywhere. If carbon separates and sinks, it can release gravitational energy, but we do not know whether it is a trickle or a torrent. We also do not know how storms die on Neptune, and that ignorance is surprisingly deep. Dark spots may dissipate, or they may slip beneath changing haze and cloud decks, leaving only subtle temperature anomalies behind. Are these storms like hurricanes that exhaust their fuel, or like vortices that survive until they are disrupted by shear and turbulence? These unknowns matter because they are the levers of the central question, and they connect surface spectacle to interior accounting. Neptune's winds and storms are the visible bill for an invisible interior budget, and the numbers must add up. When we watch clouds accelerate, we are watching energy being spent, and we still do not know the full list of deposits. A cold, dim planet can be violently alive if it stores heat efficiently and releases it unevenly, and Neptune seems built for uneven release. It can also be alive if internal chemistry keeps reshaping density and conductivity, changing how convection organizes itself. That is the unsettling lesson. Quiet sunlight does not guarantee quiet physics. Neptune's system hints that change is ongoing at every scale, and the hints reinforce one another. Triton vents, rings evolve, the magnetosphere shifts, and storms appear and vanish, and none of these processes is truly isolated. The planet, its moons, and its dust form a coupled system, trading energy through gravity, radiation, and magnetic forces. Next-generation observatories will sharpen the remote view, and they will do it with time as well as clarity. The James Webb Space Telescope can track thermal emission, chemistry, and seasonal changes over time, separating faint heat signatures from reflected sunlight. With repeated observations, Neptune becomes less like a postcard and more like a monitored climate system. Extremely large ground telescopes will resolve cloud features and ring structure with better cadence, using adaptive optics to cut through Earth's atmospheric blur. Long baselines can turn Neptune into a monitored weather world, where we track jet shifts and storm births across years. The value is not only sharper images, but the ability to watch patterns evolve rather than merely exist. But remote sensing cannot replace in situ data, because some measurements require touching the environment. The decisive measurements require an orbiter and an atmospheric probe, instruments close enough to feel gravity variations and sample gases directly. Voyager gave us a flyby, and a flyby is a glimpse, not a diagnosis. An orbiter could map gravity harmonics precisely, testing wind depth and interior density structure, because gravity subtly changes as mass shifts and flows. It could also measure the magnetic field for years, not hours, building a time series that reveals how the dynamo breathes. With repeated passes, small discrepancies become signals, and signals become constraints. A long magnetic record would reveal secular variation and constrain dynamo location. The way Earth's field changes reveal motions in its core. It would also map how the lopsided field drives auroral and plasma heating, which can feed back into the upper atmosphere. Even at Neptune, space weather is a form of weather, and it leaves signatures in ultraviolet and radio. A probe could measure noble gases, isotopes, and deep abundances that spectroscopy cannot pin down, because many key species hide below cloud decks. Those ratios would reveal formation conditions and mixing history, telling us where Neptune gathered its material and how much it borrowed from different reservoirs. In planetary science, isotopes are fingerprints, and fingerprints can survive long after surfaces change. A probe could also measure temperature profiles, cloud layers, and vertical winds directly, and those profiles are the scaffolding of every circulation model. That would connect the visible jets to the deeper energy pathway, showing where convection starts, where it stalls, and how condensable species shape stability. It would also tell us whether Neptune's atmosphere is layered like a cake or mixed like a boiling pot. Together, orbiter and probe would turn a single flyby into a living monitored system, and the difference is transformative. They would let us watch storms evolve while measuring the engine below, linking cause and effect instead of guessing. The goal is not only to see Neptune, but to understand why it behaves as it does. Mission concepts exist, but the challenge is time and distance, and those constraints shape every engineering choice. Neptune demands patience, because travel takes years and communication is slow, and power is scarce in the weak sunlight. Yet the payoff is unique, because Neptune is the solar system's best ice giant laboratory, and it is the nearest example of a planet class that fills the galaxy. So we return to the opening hook and strip it to its physics, because awe becomes deeper when it is earned. Nearly 3 billion miles out, a blue world screams with winds and hides an electrified ocean, and those are not metaphors but measurable realities. The central question remains, but it is now framed by evidence in orbit and by gaps we can name. Neptune stays violently alive because it is still cooling, still differentiating, and still converting hidden heat into motion, even under a dim sun. Triton's capture shows that the outer solar system was not quiet, and that a single event can rewrite an entire satellite system. Neptune's rings show that even today debris is being sculpted and renewed, and that the present is not merely leftover past. The crooked magnetic field shows that the interior is conductive and churning in a shell, and that convection can organize itself in unfamiliar ways. The storms show that the atmosphere is coupled to that deep churn, translating interior heat into visible speed. When we watch a dark vortex form and fade, we are watching the planet spend energy in real time. Neptune is not a quiet endpoint, but a living engine at the solar system's edge, and it forces us to revise what cold can mean. It proves that near darkness can still host power, change, and instability, and that distance does not equal dormancy. What we call beauty is methane-filtered light and high clouds, and what we call terror is the same system, seen through its winds, its tides, and its pressure-driven chemistry.